have this huge stage. I'm going to stand in it for about 30 seconds and then I'll sit down. Welcome, everybody. Thanks for coming. My name's Matt Turner. I guess you all want to learn about Istio. So this will be a look through Istio. We're going to be following the life of one packet, kind of in one side and out the other. I think that's quite a good way to understand what actually goes on in Istio, to understand what all the different components do as we go through it. I have subtitled this talk a deep dive. 3 hours is a long time. We'll see how much of that we use. And the 3-hour lecture is a really weird format. I won't be able to speak for that long. You won't be able to stay awake for that long. So we will take breaks where people can go get coffee. And don't worry about walking out at any point, obviously, to go and find the bathroom or whatever. Is my English okay? If I speak too fast, if anybody can't understand me, just wave. I know it's not everybody's first language. Other than that, as I say, I really want to prance around this stage, but I can't do it for 3 hours. There's some 4DS screens down there, like you could have had water in your face and everything. Everybody's falling asleep. But no. Right. So why should you listen to me? I'm a software engineer at a stealthy startup, currently doing service mesh stuff. I work with a bunch of the old Istio team from Google. Before that, I was a Kubernetes consultant, so I hope I know that stuff fairly well. And before that, I did DevOps at Skyscanner, so if anybody's coming on a cheap flight, those guys are pretty good. Before that, I worked at Cisco, just to say that I did not work on networks. I didn't go anywhere near one, not my specialist subject. Don't hold me to anything on that. So, what are we going to do today? We are going to learn how a packet gets through this whole Istio system. You can't really avoid sort of talking about Kubernetes when you do that. And we'll look at the Envoy proxy component as well. As I say, the style of this talk is that we'll follow left to right, and we'll look at the sort of control plane calls that are made in that process, which control plane components are included. And hopefully that gives everybody a useful mental model for reasoning about and debugging Istio should it come to it, although quality's a lot better than it used to be. I've tied myself to the chair. I'm not one of those professional speakers. Like I don't have a brand or anything. I can't even sit down competently. Who's heard of Istio? Good. Who's played with it a bit? Sort of using it? Okay. Anybody using it in production? Cool. Well, we'll dive deep. We'll start high, I hope. And as I say, hopefully this will be a useful model, because otherwise you can just throw pages of YAML at this stuff, and it mostly works, but you don't really understand why. So hopefully this will be an enlightening session. I think it's being like live streamed, so I probably shouldn't eat any more lunch either. So as I say, we will take some breaks. We'll do 3 sections. We'll look at networking and containers and Kubernetes pods and what they really are and how they work together, because that's fairly important to how this whole thing holds together. Then we'll take a break. Then we'll look at the pilot component and its role in ingress and in routing traffic around, routing. Then we'll take another break. Then we'll look at the Mixer and Citadel components and just touch on the egress component as well. So that networking and containers section. First thing we're going to do is just do a little recap of how all of this works in Linux, because it's these kind of fundamentals that I think sometimes trip people up. You know, when it doesn't work, we say Istio is this layer 7 overlay network, right? This 0 VPN shiny future, and then when something doesn't work, you're like, wait, where does that IP come from? So I'm going to do the world's quickest run through of another talk on how networks actually kind of hold together in Linux and what all of this means. So your grey box, that's about 50 feet, isn't it? Your 50-foot grey box here is a host, right? A physical machine or a VM or something. And the blue arrow there is a network interface, right? It comes from the outside, goes in, and it's got a plug on the end rather than a socket. I don't want to use the male-female analogy, but it's a positive thing. It can kind of plug into something. Right, so this is a network interface. It used to be called ETH0. It would now get some name based on its bus position, right? We can give it an IP address. That's good. We can then use that IP address. We can use the system called connect to let something like ping connect out of our system and go ping Google, and then the source address on those packets will be 192.168.0.10. So far, so CS 101. The other major system call is bind, which lets us have packets coming in, right, receive them, so something like Nginx could bind to that IP. We can give it a second IP address if we want to. This is a bit weird because this is on 2 different subnets. That's less weird than having them both on the same subnet. You can do this, but why would you? We can take a second network adapter, plug a second PCI card in, get an ETH1, give that a separate address. Right, and we can tell Nginx just to bind to that one instead. Maybe ETH0 is our kind of management backdoor. So what is that thing? Well, it's an interface. Interface means, right, an adapter, a meeting between 2 things. So in this case, it might be one of those, Intel E1000 gigabit cards. It could be ATM. It could be, we're interfacing. The important point is we're interfacing this kind of ETH0 thing, which is actually quite a high-level abstraction, onto something that knows how to flip volts on a line, which might be Ethernet, might be ATM, might be whatever. So there's a hardware part of that, which is your PCI card, and then everything on the right is really the figment of the imagination of software of the Linux kernel. So we could have another interface, foo0, but maybe that's not an E1000. Maybe we just made that up, right? Maybe that's purely got that software side. So what could that be? Where could that thing get its packets from if it's not got a transducer looking at volts on a wire going up and down? Well, we can put a process behind it. Let's call it the packet daemon. We could put a user space process in Linux behind it. We can then give that interface an IP address, and then ping can talk to that. So ping can talk to that IP address, and rather than reaching out to Google, where Google servers know what to do, it's actually quite simple. It's like a page of C to write this packet D program such that it recognizes exactly a ping request and dumps exactly a ping reply back onto the wire, right, where this wire is virtual because it's a ton. This is often used for VPNs and whatever. This is a much longer talk we won't go into. So maybe packet D spits out packets that do something, and I want it to talk to the real internet. How do we connect them together? Well, we can nap them so that anything packet D says appears to come from that 192.168.0.10 address, just like ping did, right? Or we can turn IP forwarding on, or we can route them. Your packets will get out. Nothing will get back unless everything outside of this box knows that 172.16 is inside this box as well as 192.168. So something outside needs a static route setup, or you need to be using BGP to advertise that whole subnet, etc., etc. The other thing we can do is we can turn that ton into a tap. Notice the subtle change, and give it a MAC address as well. So it's now got like a layer 2 address, a layer 2 presence. At that point, we can do Ethernet style stuff. So we can also fake up in software like a switch, all right, a bridge, an Ethernet bridge. Linux kernel will give you one. And we can then take those 2 things. Remember I said they're kind of positive, and we can plug them into the holes in that bridge, because the bridge is just full of sockets. At that point, they're kind of subsumed. They don't really, your management interface gets a bit funky, but you can't really sort of see them or use them in the same way as normal interfaces at that point. You certainly can't give them an address. So only sort of dangling arrows, if you like, can be given an address and can be bound to and connected through. These things are plugged into a bridge, so they're no longer sort of free for you to do something with them. Which means that, like, how does anything else, how does ping on this machine? You talk to the internet. So luckily, every bridge comes in with a built-in interface, given the same name as the bridge, which can be really confusing. If you do an ifconfig on a setup like this, and this is really common if you're using Docker or VirtualBox or something, your CBR0, that's not listing you the bridge, that's listing you the sort of intrinsic plug that every bridge has, which has the same name as the bridge. That'll confuse you. So we can give that the IP address, and we can carry on using it. But also, on this network now, not only was whatever's plugged in, whatever that PCI card is plugged into, we've got a little virtual bridge inside, and we've got packet D just pinging Google over the same network. Open vSwitch is another implementation of bridges. Great. So what if packet D was slightly more interesting? What if it were this other user space process called QEMU? Right? QEMU is an emulator. Or with KVM, it's a hypervisor. So it's a virtual machine, right? It can run an entire operating system within it. So within that QEMU thing, we can have turtles inside of turtles. We can have the whole thing going on again, an emulated E1000, another copy of Linux, another grey box that thinks it's got an ETH0, thinks it's got a an interface, right, and it can just use it. So the host is on the internet on 168.0.10. This VM is on the internet on 168.0.11. Right, and this is just sort of basic VirtualBox networking setup. We don't have to emulate a PCI device. We can make it go faster. VMs are a bit old. We're here to talk about Istio, right? I mean, we were moving to VMware in 2005. Everybody's been through Kubernetes and Spring Boot and all of that shit since then. So why am I talking about this? Well, imagine if we replace that VM with a container, because containers are cool. So this orange box is a container. It isn't a VM. It doesn't have its own kernel, as we know, but it can have these two user space processes in it, say, ping and an nginx again. The only difference is they're namespaced, right? They're within the namespaces of this container, which we'll come on to. But currently, they don't. One of the things that this namespace does is it isolates network resources. So those things can't see BR0. Ping cannot use BR0 to connect out. Nginx can't bind to it because they're in that orange sort of firewall, almost literal firewall. So what do? Well, imagine we can invent yet another kind of network interface that we pull out of thin air. It's a thing called a VETH, or a VETH, a virtual Ethernet pair. And it's two of those plugs, right, with a BISA string between them. So anything you put in one end, you get out the other. They're floating, so we can give them IPs. Right, I could now literally tell packet D to bind to that .1 address and then use ping on the 2, and I just get responses from myself over this piece of string. That's a figment of the kernel's imagination. Why do we care? Well, I can plug one end into the bridge. I can move the other end into that namespace. Suddenly ping and nginx can see it, right? And I rename it to ETH0 so that they have no idea they're not on the main host. Okay, and the rest of it's about VLANs and like Mac VLAN, and we don't care about that. So that's how container networking works in about 30 seconds, just so we're up to speed. I think I now have another one. Right, so Kubernetes networking. Apologies if I'm teaching anybody to suck eggs here. So 2 hosts, 2 Kubernetes workloads. Everybody's familiar with Kubernetes, right? Yeah. You can use Istio outside of it, but all of the examples are going to be kube here. It is a lot easier. But there's this kind of layer beneath that we just need to bear in mind. So 2 physical hosts, 2 worker nodes, an etcd, which is Kubernetes sort of data store control plane, and then so let's say 2 containers on each. So a foo service that's highly available across both workers and a bar. Oh no, 1 bar and 3 foos, because. So how does bar talk to one of the foos? Well, maybe it finds a foo on a different worker. How does that work? It's magic. So remember, all those things got is a VETH pair. One end's plugged into here, one end's plugged into a bridge that you can't see, but the bridge is plugged into this, connection out to the internet. So it could call Google down here. But that's no good because foo's on this other machine, and we don't want to get into BGP and all of that nonsense. So we don't really want to set that up. So how do we do it? This is where a thing called kubeproxy gets involved. So when you're in Kubernetes, right, you've got a deployment, creates pods. That's your sort of workload side of things. And then almost entirely separate is the service construct, right, the service resource. And what that gives you is a VIP. So every time you make a service, it gives you an IP, but it's a virtual IP because none of these pods take that IP. It's just in some weird range that you can sort of fling packets at, but nothing's ever going to respond to an ARP. Nothing's ever going to say, oh, I've got that IP, that's me. So what it is it's this fake sort of cluster IP here. So bar tries to send a packet at that. That would just keep going out of your default route. It would end up sort of heading towards your ISP, and then your ISP would say, what's that, and drop it. So what kubeproxy does is it installs some IP tables rules, intercepts that thing and says, right, I know where that is. Let me get it first to the other worker node, which is what actually the main job of your Kubernetes overlay network, right? There'll be some kind of tunnel here, or actually in Calico's case, this is BGP, but whatever it is, it's hidden, right? It could be GRE, it could be actual VLANs, it could be, I think, VXLANs is used by Weave. It doesn't really matter. Your overlay network plugin, your CNI plugin hides that. So kubeproxy just says, well, I saw you aiming for that cluster IP. That doesn't exist, but what it means to me is you want one of these foo pods. Let me go pick at random the IP address of an actual foo pod, change out the destination address of that packet and put it back on the wire, at which point your overlay network, it's your overlay network's job to work out which node it's on and actually get it there over some kind of tunnel. But the pattern always looks like this. This was super slow, so kubeproxy used to be a proxy on the wire, used to sit in the request path. That's super slow, so what it does now is program IP tables to kind of send it direct and say, right, IP tables, every time you've got that cluster IP, look up one of the destinations in this other kernel type called an IP set, which is just like a hash set for IP, so it's a lot quicker to pick one at random. There used to have to be an IP tables rule per every pair of cluster IP and destination, which was super slow. So it programs that up, and then it manages to get to the one of the pods. So that's service type cluster IP, which is the default. This means foo is accessible through this cluster IP, but only to other things in the cluster, right? Only to other things on this overlay network that are going to hit these IP tables rules. If you want to expose this thing to the internet so traffic can come in, next is service type no port, which says to each worker, every worker, including the ones where the workload isn't running, incidentally, to open a particular port number. So these cluster IPs, we can, as many services as we've got, we can just start minting cluster IPs. We can just make up these VIPs, assuming your CIDR range is big enough. We just keep making them. Because these ports are open on every worker node, we just have to pick a port. It's like 30,000 and above. There are a finite number of them, but there's quite a few. So everything you want to expose to the internet with service type no port, we pick a random port number, we open it up. And again, kubeproxy tells IP tables. It gives it even more rules and says if anything comes in aiming for port 30,000, that's going to one of these containers. It actually redirects it to the cluster IP, which then redirects it to a pod. Service type load balancer is yet another step which says to the cloud provider, right, I need an ELB, because this is really annoying, right? If your user on their sort of iPhone wants to actually reach your API, they have to know all these worker nodes and their IP addresses, and these things are cattle. They'll be changing quite often, and they have to use a very weird port number that's probably not, it's certainly not well known and probably not allowed through their corporate firewall. So load balancer says, right, get an ELB, which gives you an IP address that uniquely identify this service, this set of pods. You can open like a standard port 80 because there's an IP for each of these, and then the dance continues. So the ELB is programmed and kept up to date with this set of worker nodes. IP tables redirects that to a cluster IP, and IP tables then redirects that again to a pod. It's complicated. It's a whole string of things, but it does work, and it's very composable. And it actually does its job quite well. It introduces a little bit of latency, but it does its job fairly well. The one final step, Kubernetes, you ever wonder what the ingress controller was? So the ingress controller basically says that this is better than node port, this ELB setup, but it does mean one IP address per service. You know, maybe I've got www.website.app.api. or whatever. They all have to be on separate IPs. I have to manage all of that. What if I could just have one IP, and what if I actually want, api.example.com to always be what my app uses, and then I want a /v1 and a /v2. I currently can't do that with this setup. If the v1 API and the v2 API are different services, different sets of pods, they'd have to have different IPs. So we can funnel it all through one ELB. You point a wildcard DNS name at this, a wildcard TLS certificate at this, and then the first thing it hits is just another deployment, right? Just another Kubernetes service, another deployment, but a thing called an ingress controller. So this would be something like Nginx or HA proxy. That is a layer 7 router that understands how to look at the path, like the /v1, the /v2, and then pick the appropriate backend, which is just another Kubernetes service, right? So the dance continues. You aim for a cluster IP, you pick an actual port. But ingress, if you were going for the /v2 path, this ingress controller understands how to pass that HTTP, and it would aim it at a different cluster IP, and you'd end up at a different set of pods. Okay, I hope we're not asleep yet. Networking in a nutshell. So, Istio. Anybody who's looked at it, which I think is most of you, will have probably seen this picture. They've actually replaced it with this one, which is a little bit prettier, but I don't think it shows things in quite as nice a way. So we'll be sticking with the old picture. I think we're gonna be very familiar with this diagram by the end. I won't talk about it too much at the moment. Yeah, you can see sort of, I think the grey boxes are The grey boxes aren't worker nodes anymore. They're logical services made of several pods that you can see. Each pod has an envoy. HTTP proxy is a sidecar. We'll cover that, but I'm sure that's probably not news to anybody. And then it has this control plane. So these 3 control plane components that get involved and help make all of this work. And I guess the important thing to note is that on top of that control plane is this control plane API, right? So this thing is all automatable, it's all controllable via an API. That's what, although the control plane is implemented by 3 or 4 different boxes, together they talk this one API. And it's a declarative API, so it's not just sort of SOAP commands to say turn this on, turn this off. You feed it resources in YAML format, just like with Kubernetes, that describe the state you would like the world to be in, and there's your standard sort of control loop setup that will try to get you there. Yeah, I don't like that one. For first things, I think this is missing a couple of boxes. So this control plane, like any other, I said we feed it these YAMLs. We're feeding it config. It's got to remember that config. So I think there's a couple of boxes missing. The first is it just needs a database to store this configuration in. So I've shown you an etcd there. And it needs kind of an API server. So the control plane API is a REST endpoint at the end of the day. It has to be served by something. So it needs some kind of API server. Works very similarly to Kubernetes. So in fact, if you're deployed in a Kubernetes environment, then this API server is the Kubernetes API server. What Istio does is it sort of hijacks the Kubernetes system. It uses the CRD, the custom resource definition mechanism, to define a whole bunch of CRDs, a whole bunch of its own custom configuration types, which you can then write into the Kubernetes etcd database, because the Kubernetes API server knows to expect them because you define these CRDs. You can use Istio CTL for that. You can actually use kubectl because it is the kube API server. The kube API server knows what's coming. Istio CTL is basically just a full kubectl with a little bit more client-side checking of those types that it's defined, and also a few of the imperative commands. Kubectl as well as apply, which is what you should always use, has got sort of run and expose and all of those imperative commands just to get you going quickly. All they do behind the scenes is actually run just makes the deployment and sends it up. Expose just makes the service and sends it in. So Istio CTL has a few similar imperative commands for that, but it's really the same system. For non-Kubernetes deployments at the moment, if you're going nowhere near Kubernetes, and this is worth saying. So I've gone through kube networking, and all the examples will be kube, but Istio does sort of transcend that. Istio tries to be bigger and wider than Kubernetes. So if you've seen that there's the stuff about extending the mesh, so that means having sort of most of Istio hosting your Istio control plane within Kubernetes, so you can reuse that API server and that etcd, but adding workloads that aren't in Kubernetes pods. There is also a mode where you can run this thing completely outside of Kubernetes. You have to install all your own envoys. You have to do all your own sort of traffic interception, which is something we're going to come on to. But ultimately, you can do it. There doesn't need to be Kubernetes in sight. So these control plane workloads are normally run as just Kubernetes deployments, right? They're just Kubernetes user space stuff, not default namespace, but just like anything else, they're managed through the deployment. Kubernetes brings them up, keeps them up. Therefore they can hijack that Kubernetes API server. If you don't have that, you have to run all these things manually, and you need an API server. You currently have to run the kube API server by hand, which is really hard. There's a component in development called Galley, which is going to take this over. That's all politics. We won't go there. But just to say, these are the logical parts that have to be in the diagram. If you're in kube, it's nice and easy. You beg or borrow these from Kubernetes. If you're not, it can be done. I'm not going to demo that. It's really hard. So maybe a couple more boxes missing, because we've seen service A and service B. Ingress, of course, is another big part, right? I have my photo taken. I want to stand up. I want to go dance again. So the first question is ingress. We said we see the life of a packet come through this system. So where does it start? So it starts at an ingress point, at an edge. So just like a standard Kubernetes ingress controller, this thing, we have a layer of ingress. Remember we saw with kube that we would have sort of a bank of Nginx's and everything, you get to the ELB and they hit the Nginx's first, and then they take layer 7 decisions. Istio replaces that. So Istio, one of the things it does is it is your ingress controller. You need a layer 7 HTTP proxy to be an ingress controller. Well, guess what? We've got one. It's Envoy. We don't need Nginx. So it sits there with this. This is the Kubernetes networking dance we saw before, right? Wildcard DNS in this case, load balancer, no port, cluster IP, reverse proxy, and then off again to another service, and finally to the pod. So these things sit there. So they're a proxy. They're like the data plane of ingress. They also have a ingress control component. So they have a little controller that watches for ingress resources and programs them with the actual routes that they need, just like the Nginx one. They watch. So we'll get into resource types, but everybody's familiar, I take it, with Kubernetes ingress resource. That was sort of the original way of doing it. If you squinted it, it looks really similar to a piece of Nginx config. Right, it defines like host names to expect, and then a bunch of path-based routing. That's very similar to an Nginx server, and then location block. That's no accident. Nginx was definitely the sort of default reference implementation when all of this started. It's not the most expressive thing. So that ingress resource kind, whatever it is, extensions v1 or extensions v1 beta 1 ingress is still in beta, right? It's still a beta API kind. It never graduated because nobody's really happy with it. But the Kubernetes ingress controller will watch those. If you declare Kubernetes ingress resources into your system, it will configure itself to do just what Nginx would do. But Istio also defines, and we'll see them, defines a whole set of its own ingress resource kinds to give you much more fine-grained control of your ingress. So this thing listens to either. Gone too far. So now our packet can, I don't have any music, our packet can start its reversal of the famous diagram. So the first thing it gets to do is it hits a pod. Each of these pods has an IP, right? It's already been through the whole ELB. If you're on AWS, it's been through the node port. It's been to a cluster IP that's picked one of these pods at random. And now it's got to the IP address of one of these pods, right? It's going through one of these v-eth pairs, and ends up in the pod, which is a black box, right? It's an IP address. Remember, pods can have more than one container in, but they only have one IP. So it hits that pod IP. We're guessing, I can tell you, it hits Envoy first, because Envoy has to intercept all the traffic. So how does it get there? Why does it get there and not to the service? More Kubernetes. So what is a container? There's no such thing as a container. Well, there's no first-class concept in the Linux kernel of a container, right? There's nothing with container with a capital C. Chroot is a thing. It has a syscall. FreeBSD has jails. Solaris has zones. Yes, Plan 9 is the best operating system. It had namespaces, but Linux doesn't have containers. What it does have is one or more standard user space processes. In this case, we've got an Nginx and a supervisor D, and they run just like normal, but they run in a slightly different context. So what they do is they run in these 6 namespaces, which are sort of software isolation mechanisms. So you've probably heard of the network namespace. That's become quite a famous thing. But there are 6 of these namespaces, and they isolate various software resources in the system. So remember, way back, I said that those network interfaces, they're partly hardware, they're partly like a physical PCI card, but a lot of it, that interface part, that the thing you see in IP linked list, the sort of ETH0 part of it is kind of a figment of software imagination. That's an abstraction built on top of all of those pieces of hardware, or a tap, or a ton, or a VEF, or there's actually a zillion others that those other slides go into. So those things are sort of software, and they can be viewed and restricted and isolated on a software level by the kernel. So this blue box here is actually that network namespace that does that, stops you seeing interfaces you're not meant to see. There's also a mount namespace. So this gives you a different view of the mount table. This gives you basically a different view of the file systems that are mounted into the file system, the VFS, and where. If you think about it, a container needs this because every container runs from an image, right? So you have to be able to change what you think is mounted at /. You have to be able to change what you think is the root file system because that's how you run from an image. There's the UTS namespace, which basically a namespace is the host name and the DNS domain, so each container can think it's got a different host name, which they often do. The PID namespace isolates process IDs, so you can't see other people's processes. That's when if you do PS in a container, you only see what's running in your container. User namespace isolates user IDs and group IDs, so you can't see other people's users. Also stops you signaling them. There's the IPC namespace, which is a bit arcane, stops you doing System 5 IPC calls, if anybody still uses that. Well, probably nobody does deliberately, but it's a bit of an attack vector, so they're also kind of cut off. And then, as I said, the network namespace, which isolates the software side of things. So a container is these 6 software namespaces and a thing called cgroups, if you've heard of that, which is kind of hardware isolation. So they do isolation and rate limiting of hardware devices. So actually the bottom half of those network interfaces, if you want to stop this Nginx, if for some reason it starts spamming ioctls around, and if you sit in here on a shell and type lspci, it's the cgroups that stop you seeing the PCI device that backs other network cards. It's that stops you seeing all of the CPU cores or whatever. So container, but they're also useful because they can rate limit your time on the CPU. They can restrict the amount of memory you've got. They can restrict your IOPS onto disk and that kind of stuff. So containers are cgroups and namespaces put together. So a Kubernetes pod is a bit of a weird thing. So as I say, there's no such thing as a first-class container, and you don't call, muck container or chuck container or whatever it would be to get into a container. Liz Rice, if anybody's heard of her, has a great talk where she basically builds a container from scratch. She writes like 2 or 3 pages of Go code live on stage to make all the syscalls to basically sort of fork into to make 6 new namespaces and some cgroups and to set them all up and then to fork a process inside them. And it's really interesting. So you have to do all of these steps by hand. So while you're doing it, you could be a bit clever about it. Kubernetes pods are a bit clever. They kind of look like this. So they're 2 or more, well, 1 or more containers. So let's say we've got our Nginx with a supervisor D to restart it, and we want to strap on a fluentd. So we want a logger alongside it that's going to pick up the standard out of this Nginx, send it off to the internet. We could put fluentd inside this container image, but then all of our containers are opinionated about the fact that they log and how, right? Maybe we want to put fluentd alongside some Tomcat thing as well. We don't want to stick this into the Tomcat image. You know all this stuff, right, about microservices and separation of concerns. So this is 2 containers in the 1 pod. And what's actually happening is if you think about it, they have to have separate mount namespaces because they both need a different root file system root, a different / to run from their different images. They actually both have separate UTS namespaces, so they can have different host names. But they share the other namespaces, so they can see each other's. I went too far. They can see each other's processes. They can see the user IDs that each other use, and this is important to Istio soon. They can send each other signals in System 5 IPC, and importantly, they share this network namespace. So any network interface that's in this box and is visible to one is also visible to the other. This is why pods have one IP, right, shared between. So if Nginx binds to port 80 on whatever IP it is, the one interface has, fluentd can't, because there is one interface and that port is then blocked. So expanding on that network namespace a bit, there's a few different things in there. There's these interfaces, which in this case is taking an address. Then not only the VEF pair that you rename to ETH0, also the loopback interface. So there's one loopback interface per network namespace. If Nginx starts, spamming packets at low, nothing from another pod can pick those up. Nothing, if the loopback interface is a communication channel between Nginx and fluentd, say, then some other evil pod can't come and listen to Nginx's logs. Sockets, in the sense of all the sockets that are made when you bind and connect through these interfaces and Unix domain sockets. They're namespace as well. Roots. So root table, this thing can have a different default root or some different host roots, static roots to other pods, and IP tables rules. And this is what Istio uses. So there's a different set of tables. There's a different set of IP tables rules within every network namespace. So every pod has different IP tables rules, but they are shared between all the containers, between all of these processes. So yeah, as I say, there's only one IP, Nginx can bind to it, nothing else can bind to 8080, now it's gone. So what if we replace that fluentd, that logger, with something more interesting, say Envoy? Because there's this one set of IP tables rules, we can set those rules up. So we want all our traffic is going to ETH0. So this model, by the way, is called the Sidecar model. It's this idea of taking a container like this Nginx one, right? This does one job, it does it well. It's Nginx, it serves a website, it restarts itself if it dies, that's it. It's a little black box, and it knows how to bind to port 80 and do its job. It doesn't know that the logger is there, and it shouldn't care. It shouldn't know whether the logger is there or not. And the logger comes in, and it knows how to intercept, logs. It knows how to open this standard out. Just grab the standard out of any processor there, and it does its job, and it does it well. So if we've got an Envoy, what we want Envoy to do is go and intercept all of the traffic, right? So it can do its thing, do its service mesh thing. But Nginx has no idea about that. Nginx is just binding to 8080 like it always does. It's expecting to have this solid arrow going all the way through. It's expecting to bind to 8080 of ETH0, and it thinks the packets are going straight in. Envoy wants to get involved and say, oh no, I want to, when things come in ETH0, send them to me, I'm going to do a thing, and I'm going to send them back to I'm going to get them back into Nginx. As I say, this is the Sidecar model. This is a talk about Istio. There are other service meshes. We've got Console Connect now. We've got Avi, Cilium's arguably a service mesh. It's a complicated landscape. The big competitor to Istio used to be this thing called Linkerd. Linkerd didn't use the Sidecar model. Linkerd had one proxy per host, per worker node, per grey box, and intercepted things outside of the pod, just took everything trying to exit that host through that bridge we saw, and Nginx intercepted it there. Even Buoyant, who made Linkerd, have kind of abandoned that now, and they've got a new service mesh called Conduit, Linkerd 2, which does use this Sidecar model. This is a Java conference, right? So everybody's heard of Finagle, Twitter's sort of, circuit breaking, retry, layer 7 application library. Cool. So Linkerd was basically Finagle wrapped up as a standalone, adder process. So that's the reason there was one per host, because it's written in Scala and it runs on the JVM. So it used a lot of RAM, really a lot. So you only wanted one, basically. But yeah, this is the Sidecar model. Envoy is written in C++, so it uses a lot less memory. There's no garbage collection, so it's deterministic latency and a very tight. Envoy's a really interesting thing. Matt Klein gives some really interesting talks on it. They've taken a lot of decisions that mean it has not only a very flat distribution in terms of latency, so your sort of P99 latency doesn't spike up as it would in a garbage collected language, right? Because 1% of requests come in, and when you have to do a GC run, not only do you not get that, the distribution of latencies is very narrow, so it's very predictable. That is at the risk. The trade-off is that the throughput is not quite as fast. That distribution is kind of skewed to the right, so all latencies are a little bit higher than they could be, but they are very predictable in a very small variance. That's a deliberate design trade-off. As I say, Matt Klein talks about that. It's really interesting. Anyway, so we've got this Sidecar. As I say, we want to inject it, right? Nginx shouldn't know it's there. Nginx doesn't know it's there, so we have to kind of force ourselves in and get hold of those packets. So let's look at how these pods are actually set up. So first of all, there's this thing. If anybody's ever administered their own kube, you've heard of this, the CNI, the Container Network Interface. That's the interface through which Calico or WeaveNet or Flannel or something, plugs in. And that's where kubeproxy says, hey, I need you to get this packet to this pod that's on another worker node. Just deal with it. Do a GRE tunnel or something. There's another interface called the CRI, the Container Runtime Interface. And that's when Kubernetes says to something, often Docker, go make me a container, please. Right, and it's got to be running these. Go make me a pod. And it's got to be running these containers. So the CRI engine, which is that thing that Liz Rice will take you through kind of building, builds your pod. It makes the C groups and it makes the namespaces. So let's say we've got to this point, we've got a network namespace with an empty set of IP tables rules, we've got an IPC namespace, we've got a user namespace. At this point, this thing has some kind of persistence, right? If you turn IP forwarding on a Linux machine, it's still on, like when you've finished. So you type sysctl, that's the user space command, it makes some system calls on your behalf. But when that thing is finished, when that thing just returns 0, IP forwarding is still on. Like this is Unix. This is not a declarative system. Like you issue imperative commands and things change, and the kernel remembers them until you reboot. It's the same with IP tables, right? If you write an IP tables rule, you say IP tables, the CLI returns, but the rule is still in place. So these IP tables rules have a kind of persistence. You can write these rules and then they stay there, is my point. You don't have to be sort of blocked in a system call, like asserting them. So you can kind of think of this blue box as having some sort of persistence. So what happens is Istio uses a Kubernetes mechanism called init containers. And this basically says that you get to run some containers if you want before the main ones, right? So your main container or containers in a pod are expected to be daemons. They're expected to start a long-running process, as soon as that process, like Nginx in the foreground, right? As soon as the sort of entry point of a container returns, then Docker Kubernetes goes, okay, we're done, container is finished. So they're obviously, because they're designed for batch processing work that takes an amount of time, or usually for daemons, for network daemons. But you can have 0 or more init containers, which is a container where the entry point is kind of run to completion, and then the next one's run, and the next one's run. And often these do things like they will say you've got a volume attached. They'll check if there's a file system on the volume, and they'll format it if there isn't. But we can use it for network setup. So this is defined in your Kubernetes pod definition. Istio uses 2 of them. The first one is just the Alpine image, right? So it's just anything that's got bash in, and the command it runs is kind of this, and it turns on core dumps. That probably tells you something about what the Istio team think their stability is like. I couldn't possibly comment. But this is something that's, this is sysctl, this write into sysfs is persisted, so core dumps are now on. I think that's boxed by the IPC namespace. But anyway, core dumps are now on for anything that comes after, maybe, I don't know, slightly buggy Istio components. The next thing we run is a special Istio container image, a thing called proxy init, and this has got a long shell script in that does some more complicated stuff and basically sets up all those IP tables rules to do that network interception, and then it runs to completion and quits, but your rules are there when we've gone. There's a few reasons for this to be first. Like mostly, so this thing can kind of, this script only has to be here. It doesn't have to be in any other container, separation of concerns. If this thing crashes or has an error, it's really obvious like what caused it and where. It can be rev separately. And also, because writing IP tables rules is a privileged operation, it needs root, it needs a subset of root, it needs the net admin capability. So this init container and only this are run with cap net admin. And then it quits and drops privileges. So that's nice. Because we're talking for 3 hours, I'm going to try to explain how this works, but it's really complicated. I should have taken a copy of the shell script, but it's pages and pages long. I guess what's important are the parameters to this script. So the P here is a port number, 15,001 is a port number, and then this 1337, good work Google, is a user ID. So how does it work? I've got a copy of this script here. Sorry? Yeah. Oh, actually, this script is dangerously out of date. Okay. Well, it's tedious. I had to debug it once, so I knew it. So I kind of wrote it all down when I did it. Effectively, IP tables. There's an ingress and an egress rule. So Envoy gets involved both when a packet comes in and when a packet leaves. You want to intercept all packets coming in. That's quite easy. You just put a rule goes into the main input chain, if anybody knows about IP tables, and that points you off to another chain that is called Istio redirect. All Istio does is basically take all traffic and send it at Envoy on port 15,001. So Envoy is listening on 15,000. Envoy binds to localhost, because Envoy still has to be listening somewhere. So the packet's in the pod. Envoy binds to localhost because it doesn't need to be exposed to the outside. Port 15,001. Traffic comes in, gets redirected to localhost 15,001, makes its way to Envoy. On the way out, that's kind of similar, but you don't want to go into a loop, so you need to pick up everything that's come out of the app, send it to Envoy, but then everything that's come out of Envoy doesn't want to be picked up again, because that'll still go through the output chain. So what they do, basically, is run Envoy as user 1337. And remember I said that the users pervade this whole pod, this whole space. So there's then a rule that says, well, if the packet is egressing and hey contract, if it's come from a process with user ID 1337, then skip it. That's the long and short of it. It really is very boring. We won't go into it. But suffice it to say, we get this kind of setup where the traffic gets to Envoy, actually via low, and then Envoy sends it back to localhost. It gets to Nginx, and then it does the reverse. And then we can run a write. So as I say, Envoy 15,001, but only on low, only inside. And then finally, we have the setup we want. These two final containers run. This is the setup we're used to. And the traffic interception then works on the way in and on the way out. So we've covered how the traffic goes through Kubernetes, through the ingress, gets into the pod, gets into Envoy and back. At that point, I was going to propose we take a little break, because that's a bit heavy. I'm doing about right on time. Should we all have some coffee, and then in 5 minutes I'll carry on? Cool. Welcome back. Just before we start, a couple of people come up to me. I thought I could hear some kind of music sat down here. I thought it was another room. Apparently it's maybe coming from within here. It's your conference. You pay for it. Do what you want. If this talk isn't for you, feel free to come and go. But could we please not, watch movies or play games in this room, because it is distracting people. Thanks. Cool. Let's move on to talk about ingress and routing and what that pilot box does. So, I think I've woken up a bit. The packet has got into a pod. It's been intercepted by Envoy. Envoy's done something, right? We'll actually kind of cover what soon. It's bounced in and out through service A and back out to Envoy, and now it wants to go somewhere. So let's say service A wants to talk to service B, conveniently, because those are the only services we've got on the diagram. So the first thing it's got to do is find out where service B is, right? So service B is that sort of logical grey box, but it's made of those three pods. So first of all we need to know which three pods those are amongst all of the ones, and then we need to sort of choose between them. So what service A is going to do is it's going to use as we saw, it's going to use the Kubernetes cluster IP. So the code in here will have a name like service B. It does DNS resolution for that, right? So that's a Kubernetes thing. Kubernetes runs a DNS server on an IP address in the overlay network. Kubernetes injects a etcresolve.conf into each of these pods. Your application, be it JVM, be it C++, be it whatever, almost certainly uses Linux system getter info to do the name resolution. That calls into the resolver in the C library, right? Obviously, the JVM does its own thing and breaks all of the rules, doesn't obey any of the cache times. Let's not talk about the JVM, I hate it. But a sensible system will go and do that. So they use the Kubernetes provided DNS server, which will give them resolves that name to the cluster IP, to that cluster IP that we saw. And as I say, if we just leave this up to Kubernetes, then at random it'll end up hitting one of these pods. But we can do better than that. That's the whole point of this service mesh, is that it's like an overlay network, but like a layer 7 overlay network. So it's like that Finnegal or Hystrix. If you come across that, it's like one of those application sort of services libraries, but it's out of process. So where does this packet go when it leaves? So yeah, there's multiple instances of service B. What happens? So the first thing to know about Istio is that the IP address that's used, that whole DNS thing is kind of pointless. The name service B is used. It's looked up in DNS. It's translated to an IP address. The first thing Envoy does when it gets hold of that IP address is to throw it away. It just ignores it. But of course, the name service B has also been put in the HTTP host header of the packet that's been sent out. And because Envoy's on the wire, because Envoy understands HTTP layer 7, that's what it looks at, and that's what it actually uses to route the traffic. So it has that host header. So how do we find, like, we still have to find one of these pods on the other side, and we can't rely on Kubernetes, because if Envoy just sends the packet to the Kubernetes cluster IP, it'll end up at one of these pods at random, and we want to do better load balancing than that. So we need to find, with this host header in hand, we need to find these pods ourselves, and then we can do a better job. So we've got you do need Kubernetes services set up for this whole thing to work. And the dance isn't quite as simple as it might seem. So, anyway, let me think about what I'm going to do. Sorry, I'm a bit distracted. Okay, so it's my service. Ignore the fact that this was a node port. That's a superset of cluster IP, so it's got a cluster IP. So this is a VIP, and it doesn't really exist. As I say, kubeproxy used to sit in that data path, like Envoy does. These days, it just programs IP tables, but they defer to IP set, and it picks one of those pods at random. So that's sort of round-robin load balancing, very rudimentary, and Istio can do a lot better. So we need to find the back ends of this. So how do we find them? All we've got is that cluster IP. The first thing we can do is look in DNS, right? Let's say Kubernetes exposes that, but you don't get anything more than that cluster IP. You don't get the pod's IP addresses deliberately, because Kubernetes wants to do its own rudimentary sort of load balancing for you. So this is no help. We can get the pods. We happen to know that the pods, in this case, there's a very simple mapping between our HTTP and service and the deployment for the actual workloads, which happens to also be called HTTP bin, which results in pods with names like this. So this kind of thing works. But that mapping doesn't have to be so simple. They don't have to share their name. It doesn't have to be one-to-one. So you can't rely on this. This kind of thing isn't necessarily going to work. Right, a service can be defined by a label selector. So this service is probably, app equals HTTP bin, but that can be arbitrarily complex. And what you need is you need to get hold of that label selector, and you want to run it. Luckily, there is basically a way that Kubernetes provides you to do exactly that. So it exposes a resource type called endpoints. You wouldn't normally program these yourselves. You wouldn't normally kubectl apply any kind of Envoy endpoint definitions. But they are created, they are reflected back to you. So like you would apply deployment, and then you can read back replica sets, because deployments make replica sets, and then you can read back pods, because replica sets make pods, and you haven't made either of them. You don't make these endpoints, but when you make a service, they magically appear. And what they are is there's one for each service, but it does list the actual backends. It executes that label selector and lists the back end of all of these of the service, right? So it gives you all of the pods. And of course, this is kubectl, but it can be done through the API. So this is what Istio effectively does. It queries the Kubernetes API server, which goes and looks in etcd, and it gets the backends. So here's the IPs of the pods, right? So now the Envoy on the left knows it wants to talk to one of these pods on the right. It can do better than just throwing at the cluster IP and letting IP tables round robining do it. It's now got all of these, and it can pick. So it can pick least weighted. Well, okay, so what can it do that's better than round robin? It can keep its own memory, right, and try to do least weighted or something, or it can do a lot better because there's an Envoy in, and we'll come on to this, but because there's an Envoy in the path of everything, because there's an Envoy on each side, and they all talk to this magic mixer component, which is to say we will come on to, this envoy can know how busy, like empirically how busy, a posteriori how busy each of these pods on the other side is, because they're all telling Mixer, like their envoy is telling Mixer how busy they are, because each one of these requests might not be equal. They may create more CPU load on the other side. The request, the HTTP transaction may be held open for longer if this thing's taking longer to think. So you can do, least squares, load balancing, and all that kind of stuff. So yeah, we can do a sort of a more comprehensive dump of this endpoint. So this is HTTP bin I had set up on my Minikube, and it's saying, okay, this thing's backed by pods. So like here's one of their IPs, and this is the port it's on. This is the protocol it's speaking. Right, so Envoy knows how to parse the packets that are coming in and out. And as I say, we can do proper a posteriori load balancing because we're on the data path. So that's a sort of specific example of the more general case of service discovery. So that envoy on the left needed to know which of the envoys on the right, which of the pods on the right to go and talk to. And to do that, it was programmed with that information, right? So I've kind of said, oh, envoy makes a decision, and I've said, well, it's all there in the Kubernetes API server, in this case via that endpoints mechanism. But actually, that's an instance of the more general case of service discovery. So one of the first main jobs of Istio is so everything is done by Envoy, right? Envoy is your data plane. Envoy is the thing shuttling the packets around. But what the control plane does is program them up and tell them how to do that. And the control plane programs them with lots and lots and lots of information, foremost amongst which is sort of service discovery, right? Like, hey, if you're an envoy and you're asked to talk to service B, where is it? Where should you go? So that's done by this pilot component. And this actually supports, this is kind of a service discovery adapter. So this supports a whole bunch of service discovery systems. One of them is Kubernetes. So in the Kubernetes example we've got, where everything lives in Kube, right? All the other services you're trying to talk to are in Kube. So you can just go and ask Kubernetes where they are. It's Pilot here that's every now and again. I think it actually sets up a watch, so it gets pushed, right? But you can think of Pilot kind of polling Kubernetes and saying, hey, what services are there? What are their endpoints? What services are there? What are their endpoints? And it remembers them. And then it actually stores them in that etcd it's got. And then it pushes them to the envoys. So this is the big difference between Pilot and Mixer. We'll come on to Pilot's more of an offline, occasional thing. Pilot will get this service discovery information, deduplicate it, index it a bit, and push it out to the envoys. So configure the envoy, all of the envoys, so they know what to do. So they know not least like what names exist and what the endpoints are. But you may have other service registry systems, service brokers, right? So you might be running outside of Kubernetes, in which case you don't have this Kubernetes. Your service discovery might be console, or it might be Zookeeper, in which case Pilot can do that. Or you might have a mixture. So Pilot can support more than one. And you can use more than one of them at once. So maybe you're in Kubernetes, but you do have some stuff outside of Kube, but your services want to be able to reach. Maybe you've got a big Hadoop job or a big Kafka queue or something. And the endpoints of that can be in some Zookeeper system you've got, right? And your Pilot can be configured to talk to both. So if you've kind of played with Istio, if you've installed it into Kubernetes, then this configuration to talk to Kube comes out of the box. This just works, TM. But you can go and configure it to go talk to Zookeeper and say, I've got a Zookeeper instance over there. And whenever you see, hey, I want to submit a job to Spark from one of these services, then you can look it up and it should just work. And in your case, that information might come from Zookeeper. And that'll be deduplicated by Pilot and stored and pushed to every envoy. So this is showing Envoy's a very modern piece of software. It's configured by API. It's actually got 7. One of which is service discovery, kind of name discovery. What names are allowed to be used? If I see a name in a host header, like, does it exist? Is that okay? Another one is, well, what are the sets of IPs that form endpoints for different names? Others are like, where do I get certificates from? As I say, there's 7 of them, and together Matt's been pushing them to be called this thing called the data plane API. So he's actually proposing this to be like a universal. He would like HA proxy Nginx to also adopt this, so that this proxy component can be replaced in systems like Istio and in any other system that might want to do this kind of layer 7 reverse proxying right an edge or whatever. Anyway, through the Pilot knows how to talk to Envoy, but it does talk through this API that does its best to be extensible and open. And Pilot is your sort of service discovery aggregator. And it's that abstraction between Istio and the whatever environment it happens to be running in. As I say, it's not an online call, so it's not like Service A sends an HTTP request to Envoy targeted at Service B. Envoy doesn't then have to call Pilot and say, well, what's this Service B thing? Where do I get it from? That would be a bit slow, a bit dangerous. So this is all pre-computed by Pilot, pre-known and rendered into your envoys. So yeah, Pilot sucks all of this data in, as I say, it kind of watches where it can, and it gets it in this table and has it ready to go. So anything that can be sort of predetermined by this, anything that can be pre-programmed into the envoys is done by Pilot. So if you've got 10% A/B routing, or like a fallback based on user agent, say 10% to service, when you ask for service B, 10% actually, 90% actually goes to service B, 10% goes to service B beta, unless anybody's user agent is Internet Explorer, in which case they go to a 404 page, right? That kind of setup is that can all be done ahead of time, like a priori, even though you've got that 90%, 10% split, you can just take that decision. Envoy can just, roll the dice every time, right? It doesn't actually need to ask every time. So all of that stuff is pre-computed by Pilot and pushed into Envoy. So yeah, as I say, Envoy aims to be replaceable, aims to be a good open source community member because it's got this data plane API. So finally, we're ready to make this call across, right? Why am I showing Ingress next? Oh. Yeah, let's go for that. Okay, thanks, Pass Matt. So, there's Jin on the train. So, what else could we do with Pilot? So, Pilot pushes config to these envoys, which are these sidecars. But let's remember that the ingress is also like a bank of envoys as well. They're actually separate ones. So this your ingress controller, and it's the same thing, right? It just needs to know how to do routing as well. When a request comes in from the internet and says, hey, I want service A, because service A is your sort of front end, these things have to know how to get that. Before I've just said, the packet comes in and then Istio takes over. Well, you're getting involved with Istio as soon as you hit this front door. So Pilot just configures these things as well. They're just envoys like anything else. So how does it do that? Let's have a look at some major config types. So this is where we're actually getting into sort of looking at how Istio is configured. So you've got a resource type called a service entry, and this basically says what names exist. This may sound like a silly thing to do, like why isn't every name valid? But there are good reasons for this, because this is the place where you can do rewrites, and you can say, well, you've got a name, you should know what it is, or you've got a name, this name is allowed to exist, but you're going to have to go look this one up in DNS every time, that kind of thing. So service entries say what name exists and what are allowed to be used internally. They normally come from Kubernetes, as I say. So they come from this ingestion point. Okay. Cool. I'm just going to take another break here. Sorry, I know it hasn't been very long. But I'm a little bit distracted. So you can have more coffee, and I'll get back to you, because this stuff is going to require me to concentrate, because I always get them confused. I'll be right back. Who can talk for 3 hours? I can't talk for 3 hours. Hey. Right, sorry about that. Hopefully we can cut all of this out of the video. I've been a bit ill recently. I'm a lot more ill than I thought I was, but I've taken a load of painkillers. So hopefully I'll be able to get through this without being too distracted. Cool, if a little bit high. Right, so your service entry in Istio says what names exist. And as I say, there's a bit of rewriting there. It also says which ports are valid. and allows you to sort of choose which kind of error message to return, which HTTP error code to return if you don't match a name, that kind of stuff. It's also, as I say, these things are normally populated by pilot. So if you're in Kubernetes, then Kubernetes services will be reflected as service entry names automatically. You don't need to configure them. What's kind of annoying is that Istio has taken the helpful step of deciding that to make debugging easier, they won't show you those. So if you say like istio.ctl get service entry, you just won't see all of the automatic service entries for Kubernetes names. Don't ask. But they are in there. The main reason for this is for you to be able to give extra service entries for names that exist outside of the Kubernetes cluster. So if you're doing that mesh expansion thing I was talking about, you're saying, well, in addition to the pods in the Kubernetes overlay network in this cluster, I've also got some services with envoys next to them out on some VMs. Then that's when you need to say, right, and that service is called Kafka, and so you're allowed to use the name Kafka. Here's a service entry for the name Kafka. Virtual service is kind of the next. So if service entry is the sort of Nginx server block, virtual service is location. So that's the thing that says, right, so given a particular name, I'm looking for foo, service B, how do I route to backends? So that's when the virtual service is where you say, well, let's have a look at the path, right? If you're going to /v1, go here. If you're going to /v2, go there. For any given name, it also lets you, so path or authority now in HTTP 2, well, so paths in HTTP 1 were a bit special, right, because they were on that first line. HTTP 2 really spells out that they are just, sorry, authority is host, but path is another header. HTTP 2 really spells out that they are just another header. You can think of an HTTP packet as, addressing something along sort of multiple dimensions, right? So it's like path, and then orthogonal to that, you've got host, and then you can also make decisions based on the language the user wants, or the user agent they've got, or a particular cookie or something, right? So all of these are sort of this n tuple of things you can use to route a packet to use to address the backend service. So that's what the virtual service does. It says, given that host, that authority, what else do I need to look at to pick the backend? So that is normally, the simple version is that's just a path. That's just path-based routing. And these things bind to gateways, so we'll come back to that. But the next one is a destination rule that says, okay, I've got this set of backends from the virtual service. I've looked at the path. I've looked at the fact that the user wants French, so I've picked the subset of Nginx's serving the French translation of the site or whatever. How do I talk to them? So a destination rule is where you would say, right, you are load balancing between them like this. This is you want to throw a circuit breaker. This is your retime. This is your retry. This is your timeout. This is your certificate for MTLS, all of that kind of stuff. And then you can think of the simple version of a gateway is saying, please expose this virtual service to the outside world. So the simple version of a gateway resource is it says open, because within our mesh we can do whatever we want and it's all magic, but ultimately we've got this bank of envoys, right, and they are fronted by no ports and by an ELB. So if an actual user on the internet wants to talk to our thing, we need to start punching holes in this. We need to start opening ports. So the simple version of a gateway is it says, well, punch a port open here so that the outside world can talk to me. That's the simple version of a gateway. And when I say virtual services bind to gateways, what I mean is, so that's, again, almost your Nginx server block. The virtual service needs a gateway to apply to. So a virtual service doesn't just apply to all traffic flying everywhere. So a virtual service will say, right, so you've opened, port 80 here. You are expecting www.example.com. I am the set of path-based routes for that. There is so you can have more than one gateway to open more than one port, to expect more than one name, right? So you might have wildcard DNS pointing at the front, and then you've got gateways that are, for API dot and app dot and whatever. Virtual services can also bind to another gateway. There's an implicit gateway called mesh, and that is the gateway of all of these envoys. So all of the internal interception points, all of the internal sidecars here form this gateway called mesh. So you can then make a virtual service that says, right, any traffic flying around within the mesh, once it's got through ingress and I've kind of sanitized it and it's been through my front end, anything flying around inside gets routed thus. Yeah, so a virtual service will bind to a gateway, either the implicit mesh gateway or a named gateway. If I've opened a port to the outside world, that does layer 7 routing. Destination rule then says how to talk to those backends, and a more sort of TCP level service entry introduces new names if those things are necessary. So this is kind of an example of these are 4 of Istio's main resource kinds, 4 of the main types that allow you to declare to Istio in a declarative way, like what to do, how to route. And what Pilot does is it looks at the database full of these things and all those implicit service entries it got from Kubernetes and console and whatever, and it kind of mushes them all together and programs them into those envoys, both the ingress envoys, which is why we're actually in this section, and the mesh sidecar envoys to tell them what to do. So for a bit of a diagram, right, the purple bit is a name, so you're allowed to, let's say we've got an HTTP bin in this mesh somewhere, you're allowed to use the name HTTP bin. Orange is the gateway, so this is maybe an external thing, expecting www.example.com. These two are the internal mesh gateway, and then the red is the virtual service saying, right, when you've got to that gateway, like where are we going? So to configure the actual ingress routing, let's look at some real Istio configuration. Let's look at some, and it's YAML, of course, it's YAML. Let's look at some YAML files. So the bookkeeping, the housekeeping for the metadata, Istio's got its own API version namespace. Networking Istio.io for networking things. They're still iterating on these APIs. You might notice version 0.8, if you're a big fan. Version 0.8 of Istio was long-term support. It's a bit weird for that to be pre-1.0. But the reason was they kind of thought they had the code in a good place, and they wanted to say, yep, you can start using this in production. Please go for it. Like, we guarantee this works. We'll keep patching it. But we can't call it 1.0 yet because we want to tear the API out again and change it again. And obviously, it's a major bump in Semver to change the API. So this V1 Alpha 3 stuff all came in at 1.0. That's why 1.0 was 1.0, because they did another iteration of the API. It's still in alpha. Some of it's a bit clunky. I think this gateway virtual service thing works pretty well. We'll see some stuff later that's a little bit clunky. So just like a kube resource, so this is a gateway. It's got a name. So if you've played with Istio, you've played with the book info example app, right? Almost by definition. So this is book info's front end. So this is, I want to make a gateway, so I want to punch open port 80, and you're expecting HTTP, right? When you get packets there, that's how to parse them. On port 80, you're actually opening it on the ingress gateway. That bank of envoys is the ingress gateway, and that's where you're opening the port, because you can have more than one of those. Don't ask. So go open port 80 at the sort of edge proxy bank that you've made. This is where you'd normally say, this is for my website, so this is www.example.com. This is your Nginx server block. This is actually saying, accept all hosts. This is the wildcard vhost, just because for the book info example, you tend to just use the IP address or the weird like AWS cloud name of the ELB or the ILB or whatever that you get. So this is just for really simple demo setups, but normally you'd put a real host name in here. So this says, punch this open, expect HTTP, parse it, you expect that host header or that SNI if it's TLS. And then behind that, I normally have to ask if everybody can read this, but we've got a 50-foot screen, so you should be all right. Behind that, we make a virtual service which does the layer 7 stuff and says, okay, on that gateway, that port 80 that I just punched open, this subset, all the ports, which is a subset of all the ports, all the hosts. Then for these paths, I want you to do certain things. So this rule applies to log in, log out. This is where the HTML page lives that you hit with the browser, and then this is an API, a JSON REST API view over the same thing. So this is saying if the path is one of these things, so if this gateway gets something looking for one of these 4 paths only, send it to the product page Kubernetes service on its internal port. If not, 404. If you hit another port, you get black hole. If you don't match the host, although you always will, you get 404. So this is your location block, right? And basically saying that this product page service knows how to serve HTML with the products in, knows how to serve REST, and also supports login and log out functions, and they go here. So we might have had You log in and log out URLs, go to another service called auth or something, right, which does a auth2 flow, and then puts your session, writes a cookie, puts your session in the database, writes a cookie, really simple stuff, and then anything that wants product page gets to the product page service. Right, and if product page doesn't find the cookie, knows you're not logged in, it redirects you back to the host you're on, redirects you to just a /login. The user's browser makes a request for login, and then you'd hit a different virtual service, and login would take you to like the auth service. But this is saying that the product page service here supports all four. So yeah, that's what we saw. We've seen how we can feed these configurations into Pilot. Pilot kind of churns them, turns them into, so Pilot gives you an abstraction, gives you a model for configuring this world of networking. Even the Istio people don't necessarily think it's finished because it's still in alpha, but that's the current model. Pilot pushes that to all of the envoys, so the ingress envoys and the internal those ones, but ingress admittedly also to the internal envoys. Through this envoys, object model, which looks very different. Envoy has these 7 APIs. They're very, very different schema. But the translation is done by Pilot. So what else could we do, right? Well, Pilot's here. What are the other functions that are sort of a priori where we can determine the envoy configuration in advance, push it out, and say, because envoy really does do a lot of the work in this system, and say, hey, envoy, when some traffic comes through, I want you to do special things. So we can do some traffic mirroring. V1 Alpha 3, this is just options on a virtual service. We're back to HTTP bin now. It's obviously what I was playing with. So we have a route, right? So this virtual service doesn't name a gateway, you might notice. So this is inside. So this implicitly binds to that gateway called mesh. So this is saying that any of these things, if service A tries to hit the HTTP bin, that's obviously just off the edge of this screen, service A tries to use that name and hit that, then sure, it's going to HTTP bin version 1. We're not matching any paths here, so this is all paths. That ordinate just doesn't matter. That's not part of our address. But it's going to HTTP bin as a destination like it was before. While you're at it, I also want you to send everything to HTTP bin version 2. This is a mirror, so this destination is the main service. So when this thing replies, those replies get sent back to the client. When this mirror thing, the reason mirror is special and it's first class and it's not just another destination, is that when the mirror replies, that traffic gets black holed, so your client doesn't get the 2 replies. But this is a really good way to start teeing traffic off for production testing, right, or for audit logging or something. We can do traffic shifting. So again, this is relying on this subset thing. Maybe imagine this was a host that was like reviews-v1 and reviews-v2. Imagine you had 2 separate Kubernetes services, because I haven't actually gone into subsets. But you can configure Istio yet again to say, well, these things are probably being managed by a Kubernetes deployment. Kubernetes is probably doing a rolling update. So I've got 2 separate container images, right? I've got one deployment called reviews. It's in the middle of a rolling update, so some of its pods are v1, some of its pods are all the way up on v3 apparently. There's one service called reviews, right? So one DNS name, one host authority name here for reviews. But we can configure Istio to tell it, because it's so tightly coupled to these service discovery systems, Pilot offers a lot of functionality. We can tell it, to recognize tell v1 and v3 apart by looking at the container image or the labels on the Kubernetes pods. Like Istio has that in-depth knowledge of Kubernetes. So I haven't covered that configuration, but assume we have. So we can say, okay, 50%, roll the dice every time, 50%, we'll flip a coin, 50% of traffic goes to reviews v1, however that's being identified, 50% goes to reviews v3. Again, not an online thing, just a sort of stochastic thing. So in order to do, say, a rollout, or in order to do an A/B test, you would, manually, you would have to slide these values. This would need to go from 0, 100 all the way through to 100, 0, like via 50, 50. You can do that manually. You can keep reasserting. You can keep applying these resources over the top. This can be driven by your CD system, right, by some workflow system or whatever. Or actually, the guys at Weaveworks have just written a controller for this. A Kubernetes controller that's going to do the the shifting of the traffic from one side to the other. They've called it Flagger. Shameless self-promotion. They're coming to reveal it at Istio London next week, which I help organise. But that thing's actually been a long time coming, to be quite honest. At the moment, there's kind of a glaring omission in Istio is you do have to change these weights manually. But that's, so from a user point of view, you know, that's a bit glaring. But if you think about how this system works, this goes into the database, Pilot picks it up. Pilot says, hey, Envoy, you know, this is how you tell these two different types of pods apart, and you just want to roll a dice every time and send 50% here, 50% there. As for canaries, well, okay, what is a canary? Like philosophically, it's really no different from sort of macroscopic traffic shifting or A/B testing. There's no first class canary resource type in Istio. I mean, the way to do a canary is just to send a really small amount of your traffic. So this is another thing you can't really do in Kubernetes, because you have to defer, because you just have to let those IP sets pick a pod at random. If you want 1% of your traffic to go to a canary, your only option is to have 100 pods, right? Have 100 pod, well, have a service whose label selector points at 100 pods, one of which is on the new version and 99 of which are on the old version. That's really the only way to do it in Kubernetes today. Istio can do this, well, okay, could do a 90-10 split between two pods. Right, it's just got these two backends, and 10% of the time it picks that one, and 90% of the time it picks the other one. Or you could have 100 of each on each version, and 10% of the time it'll pick one of these 100, and 90% of the time it'll pick one of these 100, because Istio is on that path and it's at a higher level. And that decision about where traffic goes isn't a side effect of just picking an IP at random. It's a decoupled thing, and Istio is a layer above, giving you a lot more value. Yeah, so you can do a canary even with just two pods by sending a very small amount of traffic. Or you can, it does have to be specified as a percentage. I think you can't just say like, you know, one of them, but you give a percentage. Or of course you can do more advanced canarying. So because you've got all of those headers to look at, they can all be considered part of the address that the packet's looking for. Then if there's a specific header, if the user's got a cookie because they've opted into your beta, if they're on like Firefox alpha stream, so you've decided they're an early adopter, if they're in France, you know, whatever you want to do, you can switch on that. Circuit breaking. So circuit breaking is a destination rule. So this is in Istio's model of the world. It's like, okay, your name exists, fine. I've looked at all your other like address ordinates. I've looked at all your other headers to decide which set of pods we're going to. So we're going to this Kubernetes service, but how do I talk to it? So something like a circuit breaker will be part of that, right? How do I make that last mile TCP connection into the pods? So I have, and these things are optional. If there isn't a destination rule matching something, then packets get sent. They don't get retried, you know, they don't get circuit broken, braked. They just get sent. But this is saying, right, I want, they call it outlier detection, but I want a traffic policy that says, okay, if this thing has, like, this is quite aggressive. If this has one consecutive error within a second, then I want you to just boot that one pod out of the pool for 3 minutes. Because I assume it's, you know, it's jammed up, it takes a bit of time to recover, I assume it's just dead, and it'll fail its Kubernetes health check, and then Kubernetes will restart it. You know, Istio isn't magic. You have to know how your system works. You have to know the semantics of your system, like whether things are restarting, whether there's a, you basically have to know how to talk to them, but this is how you tell Istio, this is how you model the world to Istio. And this is all stuff that we're looking at this now because this is all stuff that Pilot can do, and Pilot can pre-program Envoy. Envoy is a very smart piece of kit. It knows how to do circuit breaking. In fact, we kind of leaked the abstraction here because Envoy calls it outlier detection. So that's where that slightly wonky terms come from. So that's leaked through into Istio's model. You can also inject faults. That's done at a virtual service. Couldn't entirely tell you why. But okay, we want ratings from Bookinfo this time. So host error ratings. You're going to ratings, you're going to V1. But by the way, 100% of them are just to be delayed by 7 seconds. You'd be amazed what this kind of thing picks up. You can also, of course, inject HTTP 500s, 503s, 501s. You can fake up 401s. You can do anything you want, really. But yeah, fault injection. So you could have sort of a 1% 500 return rate. That's really good chaos monkeying. Right, so you can chaos cube to kill pods. You can, I guess, chaos monkey in AWS to kill worker nodes. At every layer of your stack, you can start injecting faults. So you can just start pumping 500s in here, or you can simulate bad latency, and you'd be amazed the kind of cascade effects you get if you start doing this. You know, ELBs on the front end will have a shorter timeout than this, and then you'll get 503 gateway errors, and you just won't understand why. This is a really powerful thing that Istio can do for you. But again, it's an Envoy thing where Istio is not on the data path. Envoy's the thing on the data path. So you tell Pilot, and Pilot just translates this and tells Envoy how to do it. But a subset of Envoys for a subset of sort of source and host addresses. And that all depends on what you put in this destination and what gateway you bind it to. So this is how the Istio model translates down to the Envoy model. So, are we done yet? No. What are these lines up to Mixer? So we've talked about the stuff that Pilot does, right? But Pilot has the lines pointing outwards. Pilot crunches configuration and pushes them to the Envoys. But what are these red lines to Mixer? So the docs say that that Istio, that the Envoys make policy calls to Mixer. And that's true, but that's a bit hard to parse unless you really know what's going on. Basically what it's saying is there are some decisions that can't be made based on static information, right? So there's some things you just can't push to an Envoy. So the set of services that exists, the set of names like service B, hopefully changes pretty slowly. Probably changes on human time, on the order of seconds or minutes if you're doing well. The set of pods, that back those services, changes a bit more often on a big system, but it's not all that fast. So that could be pushed out by Pilot. If you're doing an A/B test, you're probably changing your numbers every week or something. But some things change a lot faster. Some things can't really be pre-programmed every time and do need to be looked up by a sort of dynamic call like this. So something like a rate limit, because what Istio can do is it can do global rate limits. This is where it gets a lot more powerful than just Kubernetes normal networking. Is all of these instances of pod B, of service B, can share a rate limit of, say, 1,000 a second, right? Just thinking, well, I've got an autoscaler. Why this is not very cloud native. If I want more capacity, I just add them. But maybe they're calling a database behind the scenes, right? And they're just going to overload that. So maybe we just want to, no matter how many instances of service B we've got, right? Well, you might have more if you're all of that, depending on how efficient the latest build of the code is. But there can only be 1,000 requests a second in, because I know that every call in results in 2 calls out the back to the database, and that database is 2,000 kbs max. That's what the DBA's told me. So I can do a global rate limit across all of those pods, which is super, super powerful. And because I'm at layer 7, I can do a global rate limit from all the people on Chrome, right? This is the kind of stuff I can do, but that can't be pushed into the envoys. Those envoys can't make that decision on their own. Like, no individual envoy can roll a dice to work out whether the rate limit's been exceeded or not. Because stochastically maybe it could guess, but like to do it properly it can't. And that information changes really quickly. I might this request, this rate limit might be sort of thousands of QPS, requests per second. So, and also things like ACLs, access control list, right? You want those decisions to be made real fast. You want them to be checked every time. So in that case, there are some online calls, and they go to Mixer. So that explains what those lines are for. That hopefully explains this slightly, well, this tells us why this slightly weird architecture exists. Anybody who's sort of done any distributed systems might look at this and start screaming and say it's a single point of failure, it's a bottleneck, shit, this is on the hot path, this is going to add latency, all these kind of problems. It's not that bad. So we're going to take another detour. We'll have another coffee break soon. But before that, we'll take another detour into kind of why it's built like this, how this actually looks quite a lot like some Google internal systems that are very reliable, and why it's probably not as bad as you think. So, last recap of the day. Remember the internet protocol? So this layer 3 thing, any IP flow, so any connection over IP can be identified by a 5-tuple, by a set of 5 pieces of information. If you think about it, if I'm streaming a video from here to my Chromecast, right, it's got a source address coming from a source port, it's going to a destination address with a destination port, and it's on a particular protocol. This is IP protocol, right, as in 6 is TCP, 17 is UDP. I'm squinting as if I don't have them written down. But you know, that's your IP protocol. So maybe I've got a TCP stream going from my laptop to a Chromecast. So these 5 numbers uniquely identify every IP connection, TCP or UDP or ICMP or whatever, on a network. The reason that's important is you've probably heard the terms control plane and data plane. These terms get bandied around a lot. They're bandied around certainly in Kubernetes, right, with the control plane controlling the data plane, which is this set of workers where the sort of data is compute. Also applied to Istio. The Istio diagram uses the word control plane. I don't think it actually says data plane anywhere. But these terms were used for IP routers as well, always have been. So there's this distinction between the control plane and the data plane. Sometimes this is just a software distinction, a logical thing. Sometimes these are different pizza boxes in your cabinet, right? And there can often be one control plane pizza box and then several data plane pizza boxes because you run out of physical space for the RJ45 connectors. So this control plane in an IP router, as I say, I did used to work at Cisco. This control plane in an IP router is like a general purpose CPU. It does some fairly general purpose compute. And it builds this thing called the RIB, the router information base. This is kind of like a relational database, right? So it's got multiple tables of information in multiple different schema for those information. And that takes information from all the different routing protocols, all the different adjacency protocols. So if this router is connecting your data center to the internet, right, it's going to have information coming in from kind of ARP on the inside saying like all the boxes actually plugged into it, saying what their IP addresses are. It's going to be getting BGP from the outside saying where all the routes are going. There's maybe some OSPF coming in telling it how to take short paths to particular places. On the inside, spanning tree protocol will say don't go that way, you'll cause a loop. So there's all of these different protocols coming in and telling the router information base, like if you're trying to get to this IP, where should you go? So they're all stored in the router information base. All these protocols are different. The schema of their information are different. So they're all stored in these sort of different schema tables within this router information base, which you can think of like a relational database. In my mind, this is pilot, right? Change this for more modern. What's BGP if not a service discovery system? So change these for more modern protocols like Zookeeper, and you've kind of got pilot. You've then got a data plane which does forwarding only, right? So all it's concerned with is when a packet comes in with identified by this, because this is enough to identify the flow as it's called, this is enough to identify the entire connection, and to make your decision, obviously the destination address and port are quite important for working out where it goes, right? But if you're doing load balancing with sticky sessions, or if you're doing you're on the way back out of a NAT or something, you often actually do need to know the source to work out what the destination is, if you see what I mean. And the protocol, right? Because it might say, I want to go to 111 port 12, but you can't, your UDP, that's firewalled, you can't, right? So all these things do make a difference. So this forwarding information base is more like a NoSQL thing, right? It's denormalized, it's indexed, it's fast, it's full of hash tables and constant time lookups. Because the whole point is, a packet comes in and it wants to pick in the case of a router, it wants to pick a hole to go out of, a physical hole, like as fast as possible. And to me, this is Envoy, right? So this is the data plane of Istio. This thing has just enough information in a really fast to access format to know which pod to send any particular request to. Identified not by an IP5 tuple, but identified by n number of arbitrary HTTP headers, but same kind of thing. But this data plane in a router, certainly in a big router, has actually several different layers, from a sort of fast path, as it's called, up through to a slow path. And these all trade off speed for flexibility. So the very fastest thing might be just be the top half of an interrupt handler. It might even be on the silicon in a lot of these things. So if I get a packet in, the silicon can look really quickly in a sort of piece of a contents addressable memory, like where should it go? The problem with that is it has to cache these things. It has to cache a certain number of these 5 tuples and the hole that they correspond to. That cache is only a certain size, right? So you can't have every address on the internet in that cache. So maybe the silicon or the top half of the interrupt handler will do what it can, but when it's run out of space, or if there's a 5 tuple it's not seen before, so this is a new, I'm trying to connect to something else, and you don't, at that point you have to make a more complicated decision as to where it's going, and like, because not least you have to decide whether I'm allowed. And you maybe have to say, oh, well, it's one of those 3 holes, it's one of those 3 links, but I need to take a round robin decision, a load balancer decision. You know, we're on round robin, but what was the last one we used? So you have to ask some central data store. So for various reasons, this fast path can't always do it. So you kind of interrupt, I mean, literally interrupt in this case, like up through, in these things, you then go into kernel space, and then you go into user space where you can do nice things. Like, you know, ultimately you hit this thing that can do nice stuff like allocate memory, right? So it can make arbitrarily complicated decisions. Yeah, so all the way down from like ASICs and TCAM all the way up to user space processes. So to me, as I say, this data plane is Envoy. To me, Mixer, Istio's data plane is kind of Envoy down here doing the fast stuff, and then to me, these slow paths, this higher bit is Mixer. So Mixer is where Envoy gets involved if it can't make that decision. So it's programmed up with the forwarding information base. It's got some information, so it can look at a new request and say, oh yeah, I've looked in the fib and it needs to go over there, but I actually don't know whether it's allowed. And that information, as I say, isn't pushed by Pilot because Pilot's kind of refresh rate is a bit slow. Or, yes, but I know it's subject to a rate limit, and this rate limit's every second, so I need to go check. Like right now, I need to check every call whether that rate limit's been exceeded or not. So I need to kind of interrupt up. This is a more complicated case. I need to interrupt up to a slower path. And what's not shown here is that, you know, multiple envoys, one instance of something that has the counter for that global rate limit. So to me, that's the user process. Yeah, so this is kind of my mapping onto this more traditional architecture, but this is really well proven. This scales to the internet. So this kind of works. We've just had a few of those. Everybody's wide awake, right? I have caffeine. So Mixer is, I want to move it on the picture, I want to move it down, and I want to put it more like there to show it's kind of part of the data plane. As I say, it's kind of like that user process at the top of the stack before. So Pilot does sort of rib-fib compilation, pushes information into the fib, which is in Envoy. What Mixer does is handle those sort of exceptional packets. So things like the first packet in a new flow, as in, you know, the first HTTP2 data frame containing the headers that have an authority and a path and whatever. So Mixer has 2 actions. There are 2 things that you want to do here. So 2 broad classes of action. One is check, which is basically, hey Mixer, should I allow this request through? You know, I by definition, I know where it's going to go. Pilot's told me for everything I see, like where I should send it. But, you know, Mixer, is it allowed? And is it allowed now, based on rate limits, based on ACLs, all that kind of stuff? And then report, right? Which is, you know, hey Mixer, I saw this packet, I decided to send it over there. You should probably know. Because you may well want to log this. You want to put, this is one of the main advantages of Istio is you can log every request that goes through. You can produce metrics. You can produce distributed traces. So rather than every envoy knowing how to talk to your Jaeger and your Zipkin and your whatever else, they all just tell Mixer. Mixer will talk to sort of Sysdig or something, right? Mixer will be an aggregation point for that. Because then you only have to configure it once. It holds one connection open. It can deduplicate, etc. Like that. Those are some fairly obvious benefits. So what happens is Envoy extracts certain information from your packet. It recognizes the protocol. You know, we saw that Pilot programs it up with, you know, for every particular port number and a given host name, like what protocol that is, how it should parse it. Envoy doesn't do on-the-wire protocol detection, incidentally, not yet, so it does have to know. But it knows what protocol to expect. It parses the packet, and it sends salient information up to Mixer, and that's usually the kind of metadata. So you get a big HTTP2 flow, right, with a bunch of data frames. What it's going to send is the headers, or probably a subset of them. So there's a built-in, the way Envoy works, it's like a chain of what's called filters and parsers. So it's got built-in parsers for HTTP1, HTTP2, gRPC, as in it's HTTP2, but it knows how to interpret the headers a bit differently. MongoDB, Redis, MySQL's being written, I think. So Envoy knows how to parse a whole bunch of stuff. So when we say layer 7, like application layer, that's not just HTTP, although obviously that's very common. And it's extensible, like as long as you're prepared to write multi-threaded C++ 17, but there are people out there who will do that for cache. Mixer Envoy, sorry, is nominally extensible with extra protocol parsers. So you wouldn't send the whole body of the thing, you wouldn't send all your HTTP payload up to Mixer, but you do send the relevant metadata fields. Envoy also has knowledge of Kubernetes, so it also will send the Kubernetes context. So if you have an HTTP request come through here, not only will the HTTP headers be sent to Mixer, Envoy will also say, well, I'm in this pod, a part of this deployment on this host, in this zone, in this region. So all of that environmental ambient information, especially if you're on Kubernetes, Envoy knows how to go and get that, and it'll send all that up to Mixer as well. So that's how load balancing decisions can be made, sort of regional and zonal aware load balancing decisions can be made, because all of Envoy sucks all of that information from its environment as well. So all of that's sent up to Mixer. Mixer does some checks and does some reporting. It still seems like Mixer's on the hot path, right? It still seems like it's a single point of failure. And the key, and it would be, but the key to this is caching. So as I say, Envoy has this chain of filters, they're called, that requests go through to see if they're allowed. One of those filters is the Mixer filter, right? So when your Envoy is deployed in Istio, it's configured with a filter that says, you want to pass this as HTTP, you want to do this to it, you want to do that to it. And by the way, you want to ask Mixer, like you want to send all of this stuff to Mixer and see if Mixer says that's okay or not. That Mixer client, that Mixer filter is called FAT, as in it's got quite a lot of code in it. It's not just a proxy up to Mixer. What it does is a whole bunch of caching, basically, and that's what makes it okay if Mixer goes down and what makes it fast. So that's basically the job of the FAT client, and it's quite good at it. So it's quite a clever protocol. When, let's say, the first request comes in on a particular flow, we're doing some streaming over HTTP, so we see the headers. The Mixer FAT client picks that up, sends the metadata to Mixer. Mixer makes a decision and says, yes, that's okay. When Mixer sends that okay back, it sends a bunch of cache policy information with it. So it says, this is my decision. My decision is yes. This decision is either good for another 12 packets or another 500 milliseconds, right? One or the other. And it says, and you can cache this, and this is the subset of fields that you can cache on. So I know you sent me every HTTP header, but the reason this was allowed is, I'd say all traffic to service B is just allowed, right? The rule I have is that all traffic to service B is allowed. So you can cache this response, and you only need to cache it on that authority header that you sent me. So if you ever see, I know you sent me all the headers, but if you ever see anything else with authority service B, it's allowed for the next 500 milliseconds. You don't need to consider the other headers. You don't need to call me again. Anything with service B. Or it can say, that exact set of headers, only like everything you sent me, it has to be exactly that, right? It has to be this user's cookie and session ID and client and like etag and everything. So, that this decision is okay for the next 10 packets, but it's got to be precisely that guy. So Mixer can send, that protocol is very verbose. A Mixer can send those responses back with all of that cache information in. And that's what kind of makes all of this, work and hold together well, because this is cached as specifically, well, as generally as possible and for as long as possible. Those decisions are dynamically made by Mixer based on it, its knowledge of how it made that decision. So if Mixer were, so Mixer isn't called every time, right? It's normally just called for the first packet in a flow, and then the decision is good for quite a long amount of time, quite a few packets. If Mixer goes down, you've got a cache. A call isn't made every time. As for the reporting, hey, this request came through, this was its latency. All of the reporting of metrics, they're all batched up, they're sent asynchronously. So if Mixer's down, then it doesn't block the main thread of Envoy. And this sounds simple, right? But it's important. So that's all just batched up into some buffer. It's flushed every meg or something, and if it's down, then that's an asynchronous thing that'll just block and just keep trying again, but it doesn't block the main thread. So yeah, the caching gives you speed, the caching gives you resilience. Google uses this kind of architecture internally with this sort of central oracle, and it actually they've shown that it increases resiliency, right? Because these mixers could all be calling sysdig and Datadog and all these auth checkers themselves, but A, they'd be DOSing it, B, there'd be no real caching, or it would be much more complicated because you have a distributed cache, and all that kind of stuff. So Mixer can obviously cache decisions as well. Mixer can look at a flow, make a decision, tell one client, tell it how to cache it, but then the decision is ready to go in Mixer's cache too, and there's only one mixer. Or you can have several mixers in an HA. Well, you can have several mixers in an HA setup, but the envoys do some kind of source-based hashing or something. The envoys know how to hit a particular mixer. So whatever it is, all the envoys that are close, I can't remember the exact details, but all the envoys that are close to each other and therefore likely to be handling the same traffic are likely to hit the same mixer. So it's all about optimizing that cache utilization, even when you've got more than one mixer. They don't share state, but the cache locality is as good as it can be, because again, this mixer fat client takes some intelligent decisions about which mixer to go call. So that's what that looks like. That's why it's like that. It's not as scary as you might think. So what can we do with Mixer? For example, we can do service-to-service authorization, right? Authentication, identifying who those services are, that's something we'll come on to when we talk about MTLS. But assuming that the call is going from service A to service B, so assuming it's authenticated like that, then you can do an authorization to say, well, is service A allowed to talk to service B or not? The model for that authorization system is RBAC, right? Standard role-based access control that you're probably familiar with. So you make roles that say, yes, you're allowed to call, and then you put things into those roles. They become membership. So kind of same as Kubernetes, you've got a role and a role binding. This is a role from the booking info example. So this role says that whoever is in this role is allowed to perform HTTP method GET on details and on reviews, right? So this is a standard RBAC role giving permission, potency, authorization to do this thing. You then bind things into that role. So that role that have permissions to do GET on those two things, those are the two services that the product page at the front end calls. So you're saying the format of this name, this is obviously the authorization part of things. This is going to change. This is still currently looking at a Kubernetes service account, basically. So you're in the local cluster, namespace default, and then service account within that namespace. So workloads, processes in pods are currently identified by their Kubernetes service account. I'll come on to that when I talk about MTLS. But this is effectively saying the product page service. You just have to run every service as a separate service account, which you should be doing anyway. Right, so this binds them into that role. Fairly standard RBAC. You can do rate limiting. As I say, that's online, that's global. That can be more sophisticated than just saying service B's only got 1,000 QPS. It can be based on the source. It can be based on which version of service B you want to hit, that kind of stuff. It's complicated. It's 5 resources to configure per rate limit. I do actually have them all up here. Maybe I'll go through them. Maybe I don't want to put anybody asleep. But a more general point here is that, again, the API is still up in the air. It kind of leaks the implementation details a little bit, which is really good for our purposes, right? Because we're trying to take a deep dive. So this type of resource is called a quota adapter. So if you look back at this picture, if you think about it, just like Pilot kind of adapts Istio to service discovery systems, Mixer is adapting you, and it can do checks based on its own RBAC model by looking in etcd to look for its RBAC resource types that we saw. It can do checks based on rate limiting, which is what we're seeing. That's kind of built in. But it can also just totally call your random checker. It can just say, I've got this service trying to talk to this service. Hey, ADFS, is that all right? Or like, hey, random piece of code. And again, the reporting, like there's just adapters. So it knows how to write a standard out, sure. It also knows how to talk to Sysdig and to Datadog and to Prometheus and to Fluentd endpoints and all of that stuff. And you can write your own. So if you've got your own log ingester, I don't know if maybe there's not an rsyslog one. Maybe you want to write the rsyslog one. These are just adapters. So this is kind of leaked. So this is an adapter for a quota. So what this is setting up, and I'll use rate limit to explain this system. What this is setting up is it's saying, right, I want to configure an adapter to a quota system. So there's a system out there somewhere that knows how to keep quotas, right? Because quotas are actually reasonably difficult. They're multiple buckets. They're like an n-dimensional space of buckets that fill up and then overflow. And there's only one of them. So they might be external to Mixer as well. For example, you can use Redis to keep your quotas. So all of the envoys call into one Mixer, but Mixer doesn't do the counting itself. Mixer just has an adapter that talks to Redis and lets Redis actually do that counting. Because as we'll see, we do actually have like as m-dimensional spaces of buckets. It gets really complicated. But anyway, this is configuring an adapter. This thing's called a handler, which is an instance of an adapter. It's super complicated in rate limiting, but if we wanted to just do some logging, we would make a handler for, say, the Datadog logger, and that would configure the Datadog adapter and say where the Datadog instance is. Because this is actually an in-memory adapter, this isn't going anywhere. This config is quite simple, and it's just saying, right, I want you to configure the in-memory adapter, like a make a bit of memory that's got, buckets of size 500 that reset every 1 second. If this were a Redis handler configuring the Redis adapter, it would also have the address of a Redis server down here, right? So this configures that initial interface. These things, and as I say, this API, and it does leak what's going on. They're all one. There are several kinds of these adapter, but they follow a few templates because there's a few different things that Mixer can do. So they're either quota template adapters, right? So they're configuring adapters that talk to quota systems. This is one of them. It's talking to the internal memory quota system. As I say, you can also use Redis. There are handlers that configure metrics adapters. So you can say, right, because Mixer's getting information about every call, it generates metrics about it. And you can say, right, I want you to put that into Graphite, into Prometheus, into whatever of these metric systems, or an authorization system. So there are also handlers that configure adapters that go and talk to auth systems. Either the built-in, you don't need to configure the built-in RBAC one because it's done for you. But if you want to talk to, there's an Apogee integration, obviously, because Google bought Apogee. So if you want to go, especially if you're configuring RBAC for that ingress front edge, then you want to go and talk to Apogee and say, hey, Apogee, I can't model this in my RBAC system. This isn't just service-to-service stuff, but, is this call allowed? Apogee, do you think this is spam? Do you think this is a bot or whatever? Are they just their JWT checkout? So these things follow one of several different templates depending on which kind of adapter they're configuring, but they do fall into those two broad buckets, right? So authorization templates and quota templates are all just ways of checking and saying, is this call allowed? Metrics templates, logging templates are all just ways of reporting and saying, this call happened. So yeah, rate limit is complicated. Maybe I won't bother to explain all of it, but this is a handler that configures the adapter that kind of does nothing to a set of in-memory buckets. I thought that is turned off. I want do not disturb. This is the sort of definition of the quota itself. This is the thing that defines the n-dimensional space of buckets that we're using. So what this basically says is, see all that metadata you got from Envoy about the request. So we've got an HTTP request. I want you, having parsed it, I want you to come up with these 3 dimensions for my quota, right? So I've got a quota of 500 QPS in this quota system, but each source destination pair basically has 500 QPS, right? So when one source calls one destination, it gets to do that 500 times a second. And the way I realize that is to say, okay, I want you to go find one of these buckets in this space, And I want you to do that by coming up with an address, an access, a dimension called source, which has, and its ordinate, its value, its tag, if you like, is either the x44 header or unknown. Then there's the destination, which actually in this case, I want you to look at the Kubernetes app label, because that's going to tell me the most, right? Everything under one deployment, all the pods managed by one deployment should all have this same Kubernetes app label on them. If you don't have that, we'll have to fall back to the pod name, but obviously that's not great because there might be multiple pods in a particular service, and if you can't even find that, then it's unknown. Same with version, right? So this gives us sort of a three-dimensional address into a bucket for a quota. And then there's a rule that says, okay, if somebody tries to use that quota that I just talked about, then you're going to go and use this adapter configuration to go and actually store the data. I told you it was complicated. I didn't invent this stuff. So that now this whole like n-dimensional space quota system exists, and we've got one, and we can actually have more than one if we really wanted, dimensioned along different axes. Very powerful, very flexible, very confusing. And then there's a much more familiar kind of quota and binding system on the client side. So we want to be here first. So then we make an actual sort of client side quota that says, right, every time you want to do something, charge one. So this is a one rated request. Charge one of those 500 to the quota called request count. And obviously all the metadata goes with this, so it gets split apart based on these rules into dimensions. So you go find take one out of the bucket addressed by these dimensions in this in-memory space of buckets, following this sort of routing rule. And then we bind a thing into it. So we say, right, product page in default namespace uses that. Really complicated. Again, I quite like the pilot virtual service entry gateway destination rule kind of thing. I'm not necessarily a fan of these so much, but this is Istio's model for authorizing calls, either based on RBAC ACLs or based on rate limits. The rate limiting one is 5 resources. Hopefully that'll get more simple when it comes out of alpha. But this is, again, just to show you that you punt all of this into, you declare all of this into Istio's configuration system, and then it all gets worked out. It all gets rendered into Mixer, and Mixer will do all of these, will perform all of these operations for you. So that's kind of checking. That's ACL and that's rate limiting. Sorry if we got a bit lost. We know how it talks to Pilot, and we know how this information is cached and held onto to make this system actually more resilient and faster than it otherwise would have been. The other thing we can do is, because we see all of the traffic and it all gets reported up to Mixer, we can send this off to various other reporting systems. So we can make distributed traces, we can make metrics, we can make a service graph, and we can make logs. This is where, to wake everybody up, I try to do a demo. Might even have a terminal. But I thought I'd set all of this up. Let me read this. One more. So I haven't recorded this demo, so it might go completely wrong. I have scripted it, so I don't have to remember anything at 4 p.m. I've got a directory full of scripts. I've already brought up a Kubernetes cluster, a GKE one, because it's just easier. There's nothing controversial about that. We just use gcloud to bring up a GKE cluster. It's going to be quite big, because a lot of these components need quite a lot of memory. We have downloaded Istio. I've got the latest Istio, well, almost the latest Istio release, the one I tested with in this directory, and I've installed Helm's Tiller component because it's just a useful way of installing anything into kube clusters. That's how far we've got. Come on, Wi-Fi. Right, so I've got 2 GKE worker nodes, GKE IPs, Google Container Linux. I've installed Tiller into it, I think. Yeah, okay. Tiller 211 on the server side. Next thing to do is to use Helm to install Istio. So I'm using that downloaded Istio release. It's got a Helm chart in it. I'm telling Helm to install that. We're blocking because it takes a while. I've turned on these things, I think mostly because of the memory the containers use. They're not on by default, so I've turned on the tracing service, the Prometheus, the Grafana that fronts it, and the service graph service. So you might think turning those on is a bit weird. It's going to fill some time while this installs. Obviously, the envoys are always there. This communication always happens. Mixer is always there, but it doesn't have any way to send anything, right? What we're doing with those Helm chart flags is to say to the Helm chart, I also want you to deploy a Prometheus and configure Mixer to send things to it. And I also want you to deploy a Grafana that fronts that Prometheus, and I want you to deploy Zipkin so that Mixer can send trace information, or can send the same kind of logs and metrics to Zipkin, and then Zipkin will, it's Jaeger actually, Jaeger will then form distributed traces from that. There's nothing to stop you, deploying your own Prometheus system and not using their Helm chart. There's nothing to stop you configuring Mixer, to write to an external Prometheus. That's yet another resource kind. You'll be surprised to hear. And Mixer also supports being configured. You can write a handler that configures an adapter that will send to something ambient in your cloud. So you can send to Stackdriver on Google. You can send to CloudWatch on Amazon, right? But what we're telling it to deploy the sort of standard open source cloud agnostic components, just as other workloads within this Kubernetes cluster. It's one of the reasons it takes a while. I would have done this first, but you wouldn't have believed me. There we go. Cool. So no pods in default. Right, Istio system's got a whole bunch of stuff. It's got a pilot, it's got a galley, which is that new API server, don't ask. It's got a Citadel, which is the MTLS component. It's got, egress and ingress gateways that we saw, and it's got a tracing thing, it's got a Prometheus. So it's got all of that stuff here, and it's got a Grafana that fronts it. So I'm sure we've all played with book info. We'll deploy book info. It's not magic. This is going in the default namespace. Right, so while we're here, you see these, when these pods initially came up, they were running init container 0 of 1. I'm not actually running the debug build of Istio here to make things quicker, so there is only one of those init containers. It's the one that sets up the IP tables rules. That second one, first one that turned core dumps on, isn't there in the non-debug build. So there's one init container, they run through, and then the pod initializes its two containers, right? Because there's the container for whatever service this is, and then there's the Envoy sidecar. And I think they're now all running. Reviews one's a bit stuck. I don't think it matters. Oh, it kind of does. Come on. Cool. Oh, thanks, Matt. So we now throw this separate YAML at it. This is the thing that contains that gateway and virtual service definition that I ran you through before. So this tells the ingress gateway to punch open port 80, to expect any host name because this is a random demo setup, and to route, /login/product page /logout to the product page service, which is the first one. So we do that, and then we do some kubectl magic, right, to find the actual sort of front end of this thing. I haven't made this very easy for myself. Oh, okay, so I can do, yeah, I have. Right, so we can take, so this is the IP address of the load balancer that fronts that ingress. If you remember all the way back to like how do Kubernetes services of type load balancer work, the gateway's open, expecting on port 80, so we can put together a URL, HTTP, hit the ELB that's ultimately going to get us to the Istio ingress gateway, port 80, and this is the product page URL from that virtual service. All right, so we fit it with curl. We've got a 200, so we should be able to see it in a browser as well. There we go. Everybody's used Bookinfo, right? You remember how it works? You know, there's 3 different versions of reviews. Kubernetes does its random round robining, so sometimes you get black and white, sometimes you get nothing, sometimes you get colored. Those are versions 1, 2, and 3. And it's pretty much at random. In fact, it's pretty much in a line. There must be some state somewhere. Oh no, there you go, it's kind of random. Oh right, and then it told me what to do. Right, so that's up. Do I even care about pinning it? Not really. So these things are about actually, you know, I said we can declare the subsets. Let's just have a quick look in this. So this is applying this, which is basically saying, okay, I'm going to tell you, you've got this review service, right? So once we've done our routing, once we've decided through a virtual service that the place we're going to is reviews, use that name, reviews, and the service entry says that that's okay. How do we kind of talk to it on a TCP level? What pods are we talking to and how? And we've seen subsets come up another couple of times because this is a 3-hour talk. Let's go into subsets. Just saying, okay, for the host reviews, I've got 3 actual, under that thing, I've got actually 3 separate little like sets of that, subsets of that I want you to know about. I'm going to call them V1, V2, V3. The way you recognize them is by a Kubernetes label called version that's V1, like V2 and V3. But this could be version stable, beta, alpha. This could be obviously a different Kubernetes annotation name, or this could be something, I've forgotten what you can put in this stanza, but this could be something completely different. I think you can even say regions or zones, right, from the cloud provider, because as I say, Envoy knows where it's sat. So I think you could say I've got subsets blue and green, you know, and one's in this data center and one's in that one, or you can do various things like that, but you give these names to Istio to say, well, these are the subsets of this resource that you're identifying. So this demo, when I've given it before, was about, you know, doing that traffic splitting, like sending everything to version 1, so you just get the no stars version. It's quicker for me to do it. Right, so we've told it those, yeah, we're meant to look in the file. We've told it all of those different subsets exist. We can now update those virtual services to say, for example, for ratings, when you talk to ratings, you're going to go to like V1. There's no weight on this. There's no nothing because there's only one destination. So we'll now go exclusively. Go away. We're now going exclusively to V1, right? So yeah, Istio works. I hope we knew that. Oh yeah, and you can do the thing matching on a, you know, I said we've got kind of arbitrary numbers of ordinates in our like n ordinate address for where to send things. So we can say that, you know, any user logged in called Jason gets version 2 or whatever. More interesting is that we can port forward through to the distributed tracing system, which is Jaeger, and we can go look at that. I've been here before. This is Jaeger. How do you use Jaeger? Details? Oh no, product page will show me all the downstream, right? Find traces. Okay. See if you can see that. Okay, yeah, ingress gateway to product page, and then, okay, these were the spans off the back. Right, okay, that looks like a distributed trace. It's more difficult when you're on stage. Yeah, so ingress gateway called product page. Product page called itself. Oh yeah, product page in Bookinfo is a bit weird. Product page does proxy all the calls to everything else. I don't know why. If anybody could tell me that, I'd be grateful. So product page is doing some stuff, and at some point it wants to call details, at some point it wants to call reviews, but it it caused by looping back through itself, and I'm actually not entirely sure why. So that's a distributed trace. Looks entirely plausible. Whole thing's at 24 milliseconds, right? Importantly, though, this is all free. Like in case I need to give the Istio pitch, like 3 hours in to people who've come to this kind of talk, this has all been strapped on by Envoy. Right? Envoy is on the request path. It's intercepting everything. It's producing all of this information. Mixer's getting all of this information. One of the many things it's doing with it is sending it to Jaeger, because the Helm chart said, I want you to deploy a Jaeger instance, and I want you to configure Mixer to send things to it. So this is all completely, for free. You've got actual, these aren't guessed latencies, right? These are actual empirical latencies on the wire, yada, yada, yada. If anybody hasn't seen this before, hopefully your mind is blown. But all of you who are still here, you probably have. We've also got a Prometheus that's configured as a handler for an adapter with a Grafana in front of it. So this is the overall mesh service. This is the dashboard for the overall mesh. Let's generate a bit more load with a scientific load tester. And then wait a little bit. So yeah, all the it's spiked. 100% success rate, fantastic. So this is all the stuff you might want, right? This is Google's 4 golden signals. This is some use metrics for infrastructure, utilization, saturation. Okay, well there's your error rate, utilization. There's no saturation, but I guess you're meant to imply it from the bandwidth or something. But anyway, dashboards for free. We've got latencies, which are real. They're on the wire. All the information you could possibly want. Oh no, sorry. This is the service. Okay, this is the service dashboard for the. Okay, this is the details service. Sorry. Oh, so these are red metrics. Obviously, of course, they're red metrics because it's a service. Yeah. So requests, errors, duration, red metrics because it's a service. And then if we look at infrastructure, this is the infrastructure dashboard showing you the sort of health of the whole mesh. Yeah, request volume, error rates, types of errors. The stats are a little bit wonky. You have to generate a lot of load for it to, well, statistically significant amount of load for it to do anything, and these numbers will start changing and going a bit more green, I hope. This isn't quite right. I think this is all sampling stuff. This is what comes out of the box. Obviously, you can change it if you know more about stats than I do. And then the last one. It's got a kind of clunky service graph system built in. But again, just to show that it's all completely configurable, punt data wherever you want, any front end that takes your fancy. But again, this is a posteriori. So this graph has been built, and you can see it's changing. This graph has been built from the requests that actually traverse the actual network in the last actual 5 minutes or 5 seconds or whatever it is. Right? This isn't built from some service registry where a service like the principal engineer has declared what it calls. This isn't built on guesswork. This isn't built on scraping log lines. This is built on actually looking at the network traffic. And it's like using JOT, but it's, gateway calls product page calls, yeah, all 3 versions of reviews. We knew that, so I guess this information's quite old from before I pinned it. Also calls details, and the system stuff is here as well. So every time product page, let's focus on product page. Every time it wants to do something, it makes calls to policy to do that check. It makes calls to telemetry to do the log, right? Ingress talks to it. So everything's calling policy. Everything's calling telemetry. There you go. You can't do a talk without a demo. Logs. There are no Helm chart options to set up logging. I couldn't be bothered because you have to set up a... oh, this is going to go wrong, isn't it? Yes. To receive logs, it's not just Service Graph or Prometheus Grafana. You need a whole ELK stack. It's not in the Helm chart. it would take a huge amount of RAM, but trust me, you could have a CloudWatch somewhere, you could deploy your own Elk stack in the cluster or outside. You would then configure Istio to log to it, right? So that configuration would end up in Mixer. And then you'd write something like this, which is, if you kind of think about it, similar to that quota that we saw, because again, you're saying, so, all logging these days is structured logging, right? Or it certainly should be. So you've got a log message and then lots of tags. So basically like a log message, and then you're giving an n-dimensional address, if you want to think of it that way, for like a bucket to go and put it in. It's just a metric, but with a different type. So again, we can pull various parts of the ambient environment and the metadata out, and hopefully it's, getting towards the end of the talk, it's more obvious how that works and how that might be gathered. We can pull that out and we can use those as tags for our structured logs. And in this case, we're saying they want to go into I think this is a Fluent D, right? Oh, this is your kind of instance. This is your general description of how to dimension those logs. And then, then there's something that says, right, every time you try and use that logger, punt it through the Fluent D handler, which is basically an adapter telling you where your Fluent D instance is. Let's assume I set one up. Right, nearly done. So packets, packet can move across now, right? Mixer's been involved. Mixer says it's okay. Pilot's told it where to go. Mixer says it's okay within rate limit, within ACLs. So it can go, right? Maybe not. Can we send it yet? Well, we can, but it's maybe not that secure. This lady's called Eve. She wants to listen to your packet. So how do we deal with that? Well, we stick it in a TLS tunnel, don't we? That encrypts things on the wire. So, this is Kubernetes. These pods, you might be staying within the same host. You're certainly staying within the same overlay network within a VPC. I mean, there is defense in depth, but for all kinds of reasons, it's a good idea to have things encrypted on the wire. So that way, the only plain text traffic is here between Envoy and Service A. So Service A has to listen HTTP. So it's an interesting point, I guess. Service A can't be terminating TLS. Service A can't have certificates installed because then Envoy wouldn't be able to understand what it was seeing. It could get traffic to it. It could route to it based on an SNI header, but it's really not very good because it can't generate any metrics. It can't do any advanced routing. It can't do anything. So the model is that TLS, www.example.com EV certificate TLS is terminated either at your ELB or in an ideal Istio world of that Istio ingress gateway. And then remember I said the ingress is just more envoys. So an MTLS tunnel is established between ingress and Service A's envoy. And this is showing an MTLS tunnel between Service A's envoy and Service B's envoy. So every pair of envoys gets an MTLS tunnel. I'm saying MTLS, I'll explain what that is, but that gives you a bunch of things. First and foremost, it is TLS. It gives you encryption on the wire so that people who can crack their way into, assuming these are on two different hosts, anybody who can compromise any system in your VPC or can't, one of your Kubernetes worker nodes compromise a system in your overlay network, can't start sniffing this traffic. It also gives you the strong validation. So when I said that service-to-service auth is done, you have to know that it is Service A and Service B. You have to be sure of those names. It's that same authentication method that says, what service are you? Can you prove it? That's also used to sign certificates to set up this MTLS tunnel. I won't go into what MTLS is, it's too late, but it's, normal TLS is simple TLS, right? If I hit google.com with my laptop, I validate Google's certificate, so I know that the thing I'm talking to is google.com, not an attacker. Because it presents a certificate. I've got the CA bundles, the global ones, the sort of public ones installed on my laptop, so I can use that to generate, to validate the signature on that certificate. Google doesn't know who I am. I don't present Google a certificate. It doesn't authenticate me in the same way. I don't prove that I'm Matt, and I should be able to read my emails by giving it a certificate. Not least, how would it trust a certificate? It would need to be the person that signed it, or it would need to know the certificate authority somehow. So instead, it just asks me to log in, right? That's kind of how the web works. Is TLS goes one way, and then you just do OAuth or basic auth or something the other way. But because you've got your encrypted channel from the TLS, then I can just fling passwords across in headers, and it doesn't matter. Or password hashes. this system does mutual TLS, which is better because each envoy verifies the other one. So you do set up the encrypted tunnel, but not only does service A know that it's calling service B knows that it's being called to by service A. So they can then both say to Mixer, service A is trying to call me, is that okay? Mixer says yes, and you know that it's service A because you've got those TLS certificates. They, of course, have to be trustable. They have to be signed by a central authority. That's this thing called Istio Auth, which has been renamed to Citadel because everything needs a cute name. So Istio Auth issues certificates to these envoys, and they're quite short-lived. It rotates them as well. And that's how the envoys verify each other's identity. I won't go into it too much, but like, how does it know? So remember way back we looked at the ACLing stuff, the RBAC stuff, and we saw that when we want to add service A to the role of things that's allowed to call service B, we just reference it by its Kubernetes service account. Currently, that's all we've got to go on. So when an envoy calls into Citadel and says, I want a certificate to do MTLS, Citadel says, right, well, I need to work out who you are. I need to work out if you are who you say you are. All it does at the moment is talk to the Kubernetes API server and say, hey, somebody's calling me from this pod IP. Who are they? And Kubernetes responds and says, well, it's a pod, and this is the service account it's running out, because service accounts are kind of the identity domains. In future, that's hopefully going to get a lot better. So that's why everything's addressed, that's why your identities in this system are service accounts at the moment. Hopefully that's going to get a lot better soon. There's a whole protocol called SPIFFE, SPIFFE, which is about making attestations about workloads, right? About asserting and proving who your workload is. So the idea is, rather than Envoy just calling in to Citadel and saying, I'm pod B, and Citadel saying, hey, Kubernetes, and what service account is that running as? Okay, fine, that'll do. Envoy will call in with a bunch of, there'll be a SPIFFE agent running alongside this, and that'll say, this really is this IP, you can go and check out its service account, and by the way, here's a hash of the binary it's running, here's a hash of the container image, here's a hash of the kernel image, here's a token from the TPM on this box, here's a challenge response from the UB key that's plugged into this thing. So any and every way of verifying workload identity and integrity all the way down the stack, here's a hash of the here's the secure boot ID, all of that kind of stuff will be dealt with and packaged up by this SPIFFE agent, and that will be sent to Citadel, which will do much stronger checks on the identity of a workload. That's a whole nother talk. So when we've done that, we can set up a tunnel. We trust everything. Encryption is on the wire. RBAC is based on stronger identities, and the packet gets across. I did say I'd cover egress. Egress is the reverse of ingress. It's a little bit more complicated than that. When you install Istio, you basically get to say what set of IP ranges, egress IP ranges, you want the proxy to intercept for. What you often do is you give Istio just the IP of this overlay network, right? So if service B wants to make a call out, if it's hitting something within this cluster, if it's trying to hit service A again, then Envoy those IP tables rules will be programmed such that Envoy picks that packet up and it does its thing and you're still within the service mesh. If you're outside of the CIDR range of the overlay network, as in if you're trying to hit the wider internet, actually in a typical configuration, it simply won't get involved. Envoy just won't intercept it, won't get involved, and the packets will just flow out. If you do tell Istio to intercept everything and send it through Envoy, then for security, it's default deny, right? So you can tell it to intercept everything, but then service B's attempt to get kitten pictures won't work because it's intercepting everything and it won't let you talk to the internet at all without egress rules set up, basically. So if it intercepts it, it'll see a name, right? It'll see kittens.com. There isn't a service entry for kittens.com because we haven't programmed one and it hasn't been auto-generated for Kubernetes, which means that packet just won't go anywhere. And that's the default behavior, which is why a lot of people just leave that off, just constrain Istio's interception. If you do want it to work, then you have to do, and again, this is another place where the API maybe needs a little bit of massaging before it comes out of alpha. You have to add the service entry to say that this, whatever website you want to reach, whatever domain you want to reach is valid. Then you have to add you have to add a few more things. You have to add a virtual service to say, okay, well, you can't just get there, so I want you to redirect to the bank of egress proxies and then more configuration. We've got 11 minutes left, so I won't go into it, but you have to add the service entry for, say, Wikipedia, and you're saying this thing's not in the mesh, right? So, okay, there are a few interesting things here. This is why service entries are not just like why telling you that, yes, names exist, like DNS names have a regex, why do I have to give service entries? So you're saying, okay, wikipedia.org is a name that's allowed to exist. It is mesh external, so you won't have heard about it because it's not in Kubernetes. It's mesh external, which specifically means it's not in the service mesh, so there is no envoy alongside it. So you cannot attempt to talk MTLS to this thing, right? And you can't do any like explicit congestion back off that envoy like might add as a wire protocol. You can't do any of that. There is no envoy next to it. Treat it as a standard dumb layer 3 endpoint. I've told you this name exists, but again, if it was in Kubernetes, you'd know that name exists and you'd know all the IP addresses of the pods that back it because you have those endpoint resources. This thing you're going to have to just go and look up in DNS. I'm telling you it exists. I'm telling you you can use it, but I can't tell you where it is. So go and find one or more IP addresses by actually looking it up in DNS, rather than the alternative would be to give a bunch of addresses here. Then it gets more complicated because the egress API is a bit silly, and this says, right, if you're actually trying to get there, I want you to kind of like a rewrite. I want you to do, oh, okay, and by the way, this is only valid if you're trying to talk to port 443, and if that's happening, parse it as HTTPS because there's no on-the-wire protocol detection yet. And then it gets complicated and it says, well, I said look it up in DNS. Actually, I need you to sort of rewrite it and send stuff to this weird name instead. And then I'm going to kind of invent that weird name because I need to do what I'm doing is like a rewrite where I'm using a virtual service to force it through the egress gateway. Well, this forces it to the egress gateway. And then we punch a hole open to say, yes, this is allowed to traverse the egress gateway, because of course you're doing TLS, you're doing simple TLS, you're doing HTTPS to wikipedia.org. So like rewrite it to the egress gateway. Hey, egress gateway, allow 443 through to wikipedia.org and don't try and get involved in the TLS. Just look at the SNI header. And then here's the virtual service to kind of wangle those packets around to the egress gateway. And then here's another service entry to say on the far side of the egress gateway, don't go into an infinite loop, actually send it out. Not a great API. You can Google it. But another example of we have all the components, we have proxies, we know that we have this ambient gateway called the mesh, which is all the internal envoys. We have this gateway called ingress. We now have this gateway called egress. We can do effectively kind of name wrangling with service entries. We can do layer 7 routing with virtual services. We can punch holes at layer 3 with gateways. It's all the same stuff. It all goes into Citadel, Galley. It all goes into Pilot. This is another Pilot thing, Pilot and Mixer. And then you're done. So we looked at the networking, sort of bottom to top. We looked at what a container actually is. We looked at Pilot as the sort of router information base, ahead of time slow path. Well, not slow path, like ahead of time static configuration system, how that configures ingress and egress and routing, including things that are not necessarily deterministic, but can be reasoned about ahead of time, if you see what I mean, like an A/B test or a canary, fault injection. We looked at Mixer, which is the sort of online policy engine, but it's hot path, but it's not single point of failure. We looked very briefly at certificate issuance and MTLS. And despite me taking a break which I apologize for, to pop a whole load of painkillers, we made it with 6 minutes left, which is pretty good. So thanks for your time, everyone. Hope that helped.